All right. So just another plug for the Capture the Flag. It's a tight race at the top right now. Coming in first, we have Flame Wires, doing good. And then we've got Aerospace just right behind them, and Rattlesnake Recon, who I think are all off-site, and they're in third. And then we have 6DB at number 4. So tight race at the top. Today is the last day. It will close at 1700 Pacific time today, so get your flags in. There are several in-person challenges that many people have not solved. One of those in-person challenges might go up in value today. Oh, so participate. And there's, I know this is hard for us, but there are in-person challenges where you actually have to talk to people. And so, yeah, I know. You should actually do that one. As always, I'm usually sitting over in the CTF room, so if you have any questions or even, you were like, I'm too scared to get started, come over and talk to me, and I'll be happy to get you off on the right foot. So enjoy the rest of the conference and play the CTF. It's fun.
Hello, everyone. Welcome back from dinner and karaoke. For those who were in for all of the activities last night, it became obvious to me that karaoke was part of a team-building exercise for the community that I hadn't really known about. But when I got there, it was all revealed. And so, anyway, what I want to introduce today is Bradley Kuhn. And Bradley and I go back quite a ways, all the way to the beginning, when he was serving as the executive director at the Free Software Foundation. And we had a few conversations about, stuff. But I got to meet him yesterday for the first time in 24 years. But I want to let you know a couple things about Bradley right now, one of which is he's got one of the greatest job titles ever. And he's the Policy Fellow and Hacker in Residence at the Software Freedom Conservancy, which he will speak more about, but I know them as people who have provided me as the maintainer in the service of the project legal advice. And if we cheer really loud, maybe at the end, he might rap for us. Please, everybody welcome Bradley.
Thanks so much. I heard about the karaoke going around last night, and I actually have a well-rehearsed rap piece. And we'll see. Maybe if there's time left, and Eric really makes me do it, I'll do it a cappella for all of you. And it relates somewhat to my talk, which I want to talk today about the issue of software freedom and why over-the-air technologies are so central to how we got to where we are today with the rights users do have, and how we can continue to use freedom over the airwaves as a method for assuring that people have certain rights to copy, share, modify, distribute, improve, and reinstall their software. So I should start, this is not going to work, this is a USB keyboard, it's not going to work if I don't plug it in, is it? I mean, it'll work over the air, but it needs a receiver. So first of all, a confession. I have a master's degree in computer science. I am credentialed. I worked as a sysadmin and software developer for many years, but there were specifically 2 topics that I avoided completely, both undergraduate and graduate. The first one is graphics, which not what you all are into, but I did have to speak at the ex-developers conference once, and that was weird. And now here I am speaking to a bunch of signal processing people, and I avoided signal processing, both undergrad and grad school. So my level of technology on this is below yours, but I've got some game. My first job, in fact, was the sysadmin for the last division of Westinghouse. So I grew up in Baltimore, Maryland, and Westinghouse was the largest employer in the entire state of Maryland when I was a kid. I mean, a huge government contractor. They built all sorts of stuff. Now, the funny thing about Westinghouse these days, it's just a trademark licensor. So people who are in their 80s who think Westinghouse refrigerators were good in the 1950s buy products with Westinghouse on them, but it's just some random company that licensed the trademark to sell Christmas lights under the Westinghouse brand. So this was kind of the last group. There's 100 people working in this big division that was it was a big bullpen kind of warehouse setup that was made for 500 people. So you'd walk like through and there'd just be empty cubicles. It was like walking through a graveyard sometimes. But there were two projects still going. One was Westinghouse satellite telephone, which had a base station as well as obviously a handset end. And it wasn't doing that well. As it turns out, at least in 1997, 1996, 97, the only people buying satellite telephones were park rangers, which there's a pretty small market there, and really wealthy people with boats, which was basically holding the division up more or less. And they had all sorts of problems. And one of the reasons I didn't want to get into signal processing is the DSP was done by one woman. She was the developer. She wrote it in assembler. And like she sat there on this like it was, I guess it was a DOS PC, like editing it in whatever editor used the DOS in 1997, and she'd then give this little firmware that she made on her PC, and she was the one. She like did all the signal processing part of the whole satellite telephone, at least the handset side. And so I was like, I don't want to sit in front of an x86 PC and write assembler for us. So I don't want to go anywhere near this signal processing stuff. And while I was there, they used to do this in those days. When a company was failing, they would like use the final revenue to like do a startup inside the company. So they did this startup to do this new thing, which was digital audio broadcast, which they were all calling DAB. And of course, we had a lot of people on the team who were old enough. I think there's like 5 of us in the crowd who were old enough to remember Brill Cream ads, but there was this little dab will do ya. So that was the like team slogan, that they were going to do this digital audio broadcast. And there was a sense of excitement. This idea of taking what was analog and then using computers to collect the signal and make crystal clear audio. It was kind of fascinating, and I'm actually pretty proud of being the sysadmin for that team. I kept their Sun workstations working basically. I didn't actually do the product, but it was an interesting moment to be part of that and to see things switching over to digital. So anyway, I ended up going to grad school, but I still haven't done anything over the air other than this. So when I get to grad school, in 1997, you didn't register for classes online. You had a call-in phone system and you got a little paper book, and you typed in what classes you were registering for. And I had gotten to University of Cincinnati right at the moment when they had merged all the departments related to computing in any way, basically for funding reasons. And it was very funny because when you called in to register, they had a little like half-second window where they could play the name of the department. So it would say, you've registered for English department, course 201 or whatever. But they had now merged electrical engineering and computer science into one department. The electrical engineers did not want it to be called electrical and computing engineering because they wanted it to be EE, so it had to be electrical engineering and computer engineering. And the computer science people didn't want it to be computer engineering and science. They saw computer science as a separate thing. So when you dial in and register for classes, there was this woman who you'd hear her take the breath. She'd go, Department of Electrical Engineering, Computer Engineering, Computer Science, because she had to fit it in this little window designed for a much shorter name. So that's my basically the only wireless stuff I really did in grad school. And my second year, I had to choose between taking signal processing and advanced networking. You can guess that I picked advanced networking. But I didn't realize that because these departments merged, the computer engineering professor who taught signal processing also taught advanced networking. So at one point in my life, I took a test and I got an A explaining the CDMA. He made us memorize the CDMA like encoding algorithm, and we got a test on it. And I remember, maybe I got a B+, but I remember doing reasonably well on that test. But please do not quiz me now, because I do not remember. And I was just sitting there saying, I thought we were going to do we did do this cool project of like dumping data over UDP and so forth. That was more advanced networking. But yeah, I thought this guy just wants us to do signal processing in the advanced networking class. A few years later, I started thinking really heavily about issues of free software and software over the air. I went to this panel at the United Nations that they invited a bunch of people. They do these things at the UN where they put six experts in a room and then record it and broadcast it to all the UN sites. And there's like 100 of these a day. You think it's really prestigious. You go into the UN, you have to do all the stuff, and they look at your bag, and you're leaving the United States technically, even though you're still in New York City. But they have like 10 of these a day. But they did this whole panel on open source technologies, how to bring open source technologies in the developing world. And with me on the panel was this guy named Rishabh Ghosh, who later went on to do a number of, he had done some amazing things. He was the first guy to port, I think he first ported GCC to DOS. He had done a whole bunch of cool stuff in the early days. And then he had actually been selling DOS GCC-based CDs in India. He got involved in the UM. And so we're sitting there at lunch in the UN cafeteria afterwards, and we're talking about our first computer. I said, well, I had a Commodore 64. That was how I got started. And I just recently learned this. I didn't realize this as a kid, that the 1541 disk drive, the floppy disk drive, was twice the price to manufacture than the Commodore 64 itself. So it was, and that's why I wondered, why did I have to wait so long to get a 1541 disk drive when I was a kid? It was because my parents couldn't afford it. They could barely afford the computer, let alone the disk drive that was twice the price. So I had this little cassette recorder thing that you read software off of. And so it was basically taking sound waves and turning it into software. And I was talking to Rishabh about this, and he said, oh yeah, in India, there was a computer show on the local radio. And towards the end of the show, they would say, hey, we've got a new program to share with all of you. We're going to play it and get your recorder ready, record it, and then you can put it in your C64 and read it off. And I looked at Rishabh, I said, that's amazing, getting software over the air. Of course, I'm sitting in front of a modern laptop. My little Wi-Fi light's blinking. He says, you're probably getting software over the air right now. And I felt a little embarrassed at first, but I was quick enough to quip, and I said, but I can't hear it. And I thought it was really cool that in India, that's what they were doing. They were playing to get software to Commodore 64 users. They were just playing it over the radio in the audible spectrum so that you could download software and have the latest C64 program. One of the first slogans in free software, which didn't become the popular one, of course, we all know free as in freedom, not free as in price, which I think was actually not the best slogan. But the original one was software should be free, just like the air. And I actually think this was a better slogan. I started to think when I first heard this as the original slogan of free software, I thought, you know, I dabbled in anarchy as a teenager, right? So I kind of think like an anarchist. I'm like, okay, there's all this airwaves going through me, right? Like, if something's going to pass through my body, why shouldn't I be allowed to do whatever I want with it, right? If you're going to put a signal through my body, and I mean, obviously my brain can't catch it, but if I can build a device and I can stand here and catch it, why shouldn't I be allowed to do what I want with what's coming at me? If you don't want me to listen to it, don't broadcast it at me. Gosh darn it. And so I think that's one of the fundamental, really interesting things that we've looked at in free software, because this connection with free data and free information and freely available information that can reach people where they can't often be reached because they don't have wires running to their homes. That's something really special, I think, that connects up free software with signal processing and over-the-air stuff. So my true first foray into advocacy, and Eric, it's a little nerve-wracking to give this talk in front, or tell the story in front of Eric, because he's a much bigger player in this story than I was. But this strange thing happened. So I remember I talked about how, I'd been at Westinghouse when digital audio, digital radio was starting to happen. Well, by the time I got to the Free Software Foundation as executive director, digital television was fully rolling out. And this is where I really learned about the idea that Noam Chomsky calls manufacturing consent. Because this broadcast protection discussion subgroup, licensed by no one, authorized by no one, somehow stood itself up, controlled by the MPAA, the big Hollywood companies and so forth, and dragged along the electronics companies that made devices, TVs, and so forth, are sitting in a room together, and they're deciding the future policy of everything that goes over the air with regard to television. And the interesting thing, and we use this to great effect, was that they were trying to pretend this was an open and free process, that this was a democratic process that anybody could participate in. So, as it turns out, the dial-in number for the weekly conference call was public. And the public were welcome because they were saying it was a public process. Now, we had this interesting idea of like, can we insert ourselves in this process? And the question was how? Well, I don't know if I can say who the benefactor was, but there was a benefactor who came to Eric and said, you know what? Let's implement HDTV stuff in GNU Radio. And then let's assign those copyrights to the FSF. And now the FSF is basically has now become the only place in the world that has actually implemented HDTV yet. Because none of these companies, it hadn't been rolled out yet. Nobody had implemented it. So I had the sheer delight, pleasure, and honor to show up at these conference calls and say, speaking as the only organization that has implemented this stuff, we really don't think that this broadcast flag makes any sense at all. And in fact, because our software is under a copyleft license, we can't actually honor this DRM flag that you want to put in. I should step back a moment for those who don't know. The broadcast flag was a bit that was going to be in every HDTV signal, and every HDTV receiver was going to be required by law, if that bit flag was set, you could not record the program. And they were just going to make this happen. And it was so weird showing up to these conference calls because it was very early days of everything, right? So there's this guy, I would tell you what movie studio it was if I could remember. It was one of the big ones. The calls were at weird times, you know, so this guy's driving in Los Angeles on a cell phone in his car, and it's like not the like great noise cancellation Bluetooth in the car we have today. It's 2002, he's like, oh, you can hear he's holding the handset and the traffic's going by and the fan from his heater or his air conditioner is blasting and he's just sort of shouting at everybody what they ought to do. And what was so interesting we were able to do, because we really didn't have a commercial interest one way or the other. Our interest was we want people to be able to do cool things with software-defined radios. And if they want to receive HDTV signals and record them or do whatever they want with them, that's the kind of freedom we're trying to provide. Whereas the movie studios obviously want what they want. Heck, if the latest Hollywood blockbuster is going to air, what if somebody records it and it'll be digital? It'll be a perfect copy. Oh my gosh, our industry will be over. Meanwhile, the folks who were on the side of the electronics industry, this is before the ties between the electronics industry and the movie studios were so tight. Sony at the time was really the only one that was kind of dabbling in both. Everybody else were separate electronics people. Eric and I were just talking about how last night, how the guys from Philips, they really didn't feel like they wanted to be pushed around by the movie studios and told they had to implement something in their hardware, in their technology, just because Hollywood wanted it. And those were beautiful times, a time when people who built stuff would stand up to the people who licensed stuff. And it was just such a wonderful thing. I do think that if we had not had GNU Radio at that moment, and Eric hadn't implemented the HTTP stuff, which I think was kind of prototypey at the time, but we overrepresented a little bit, and that it was a copyleft implementation, so we could say there's no possibility of, your screen lock. He promised me he was going to turn that off. I'll hit shift every once in a while. Thank you. That we were able to say, we're the only ones with an implementation. This implementation is completely incompatible with DRM because you cannot put DRM into a copylefted program and make it work. Now, the FCC in the end was bullied to make this rulemaking, but almost immediately it was challenged, and the challenge went quicker than any challenge I've seen in these kind of policy situations before or since. The American Library Association never messed with librarians, to be clear, and Hollywood messed with librarians, and they sued the FCC. They just went to the DC District Court, which is actually really easy to get rulings in, and they won that ruling and the FCC gave up. My opinion is, I think the FCC already knew it was happening and didn't really want that to happen. And I really think that our copyleft implementation that we had ready to go affected that outcome. We didn't solve it. I mean, FCC made the reg anyway and then had it overturned in court. So there was a lot of people involved. I don't want to over-represent like Eric and I saved the world. But we played a big part. And the important part is writing good software that does interesting things that technologists want to use and putting it under copyleft licensing. My next foray into SDR regulation, because I'm basically a policy wonk these days more than I'm a technologist, I have to admit, was this really interesting thing that happened in 2007. So Cisco, now in the wireless router business, at the time they had just bought Linksys, or recently had bought Linksys, and they were getting deep into the wireless router business, and they did not like it that we had, just a few years before, gotten the Linksys code liberated because it was under the GPL, and now there was this burgeoning OpenWRT project. And again, 2007, OpenWRT is a young project. I should mention these days OpenWRT is actually part of our organization, the Software Freedom Conservancy. But they're a young project at this point. And Cisco, basically to kill any possibility of having open source firmwares on wireless routers, they ask this very simple question to the FCC, and because SDRs are starting to become something the FCC is paying attention to, they're like, well, we have to regulate it, and they come in and say, we believe the FCC needs to make a rule that open source software can never be put on an SDR ever in the United States. It was actually my first opportunity. I didn't talk to any commissioners, but I talked to like assistant commissioners and so forth, and it became really, really clear that at least that era of regulators, you know, they had lived through the days when Radio Shack was actually a Radio Shack, and you could go and buy components, and you could build stuff that possibly violated FCC rules, and you could get in trouble, and the FCC might drive around your neighborhood and find out you're broadcasting and get you in trouble. But they didn't see the software problem as any different than that, which was great, because they said, well, hey, if people can buy components on the open market and build something they're not supposed to, they're breaking the law, and we'll prosecute them. If people take software and do things and take the thing out of band because it's an SDR now, we'll prosecute them. And I really got the sense then. I don't know if this is still the case. All the FCC cared about is when it got powerful enough for them to hear it. Like, they didn't really care if you're going to sit in your lab and broadcast stuff that only goes 100 feet. They were, and receive stuff that only goes 100 feet. It's when you want to put a giant antenna on your roof and then start broadcasting in a spectrum you're not supposed to be in. And from their point of view, people notice that we hear that, and we can take care of it. So they did this really beautiful thing, and this is the key quote, that they admitted that, okay, there's a higher burden if you have an open source SDR, but this is worded so perfectly because it is in the context of a moment when people are publishing articles saying open source software is actually more secure. It is more vetted. We are sure it's more stable and more valuable. This is right at that moment when that's becoming a watershed in academia. So to say this just basically hints right to the open source folks like us and say, hey, it's really okay. You can do what you want with SDRs. Just you have a high burden if you want to get the thing certified because we got to be sure it's secure. But it can meet the burden. There's no specific reason, they say later in the ruling, that it can't be open source. So the sad part is that regimes change and commissioners turn over. We went through it all again. I'm not going to go through the details in the 2015 one. The 2015 one was targeted much more directly at wireless routers. But at that point, the great thing about it is that because we built up these coalitions, starting with Eric and 5 of us in 2002, adding in people in 2007, by 2015, there was a giant group of technologists coming up saying, the entire internet depends on open source wireless firmwares because if you remember the buffer bloat problem that had been solved in Linux but not elsewhere, and these technologists were able to talk to the FCC and say, you don't understand. You are going to hurt the American people if you tell them they can't use open source stuff on their wireless routers. And in fact, the rulemaking just never happened. Now, lots of the industry thinks it did, and they think that they love to point, when I enforce the GPL against wireless router manufacturers, they love to put up slides of all these rules. And I love to be able to say, well, we talked to the commissioners then, and we're real clear that that doesn't affect it, and that doesn't affect it. So where do you think that, please show us where in the rule you think you have to make your hardware locked down such that you can install new firmwares onto your wireless routers. And they can never find it because it's not there, because we made sure it wasn't there. because we were engaged in this policy work, and the free software, this is the most important thing, the copylefted free software was ahead of where the industry was going instead of behind. We were doing better things with wireless routers before the industry knew what they were. We were implementing HDTV and GNU radio before anybody else did. And that is so key. And that's why we keep succeeding in advocating for software freedom by making the innovation happen in open and free software in an academically rigorous way, in a secure way, because we know that open source is secure. And I believe we need to do more of this. So in some sense, what I want to give you here is a pep talk to keep doing what you're doing. Keep creating the new things in the open and doing the research in the open and doing the implementations in the open. Keep experimenting. I know there's a lot, how many people are hams here? I'm sure half the room, right? Three-quarters of the room. Yeah, I mean, and keep getting on the spectrums that are there for the people. I mean, the fact that we have amateur radio spectrum is so important. I hear, every time I talk to hams, they're doing something amazingly new and interesting over the amateur band. And the more of that you do, the better we are off for freedom of the airways and freedom of software as well. As I said, I was dabbled in anarchy as a teenager. I was into punk. When I was asked to give this talk, I immediately thought of this Ramones song, We Want the Airwaves. I think that we do own the airwaves with free software, and I think GNU Radio is a big part of why we do. I hope you will continue to do that, and you will have to, on occasion, thumb your nose a little bit at industry. There will be pressure. Imagine if what we said, instead of releasing GNU Radio under a copyleft license, if we released it under the MIT license, the message we would have given the folks in the broadcast flag working group, we would have said, well, you know what, we've already implemented, and we put it under a license that will allow you to take it and add your DRM, add your broadcast flag stuff to it, and we'll just keep feeding you the technology. We're not gonna put the broadcast flag stuff in ours, but you'll be allowed to take our stuff, put it in your products, and it'll be so much easier because you have this open source stuff to rely on. It was because it was under a copyleft license that it actually helped fight the issue of DRM over the airwaves. So I leave you with that. I know there are debates going on and decisions being made about what the license of various different components will be. I would be glad to talk at length in the hallway track about why copyleft licenses are going to be the better future for not just the airwaves, but freedom of free software in general. So with that, I'm happy to take questions. I work for a charity. We're called the Software Freedom Conservancy. We are supported primarily by individual donations. It's $128 a year, and I would love it if you would become a donor, an annual donor. You get a t-shirt. You also get a hand sanitizer these days, so that's thanks to me. That was a swag I wanted for this year. So you can get a hand sanitizer and a t-shirt and help support our work. So thank you all for listening. I really appreciate it. I think I've left enough time for questions. So I think Eric's got the mic. You gonna take the mic around for questions? Yeah, great. Thank you.
I am one of those hams who are doing wild and crazy things with our spectrum, but
Thank you.
It's completely invisible to the FCC. And how do we fix that? Because our gatekeeper, the American Radio Relay League, is not into all that wild and crazy stuff, although they're making progress, but they are not there about promoting new digital modes, clearing out the old analog repeaters that aren't doing anything, et cetera. Can you offer some insight?
I mean, I don't know the politics of ham radio well enough to give you a direct advice. I can give you general advice, which is decisions are made by people who show up, and activism is an essential component of getting policy changed. And being part of the regulatory bodies and running for board seats and so forth is a way to affect change. And I think that that's always the kind of thing you want to do. And I know plenty of folks in the ham world who are very excited about doing wild, crazy new stuff.
I guess my question was, I've given up on trying to influence the ARRL. They are just too entrenched with the old paradigms. But is there, I'm imagining a way to bypass. You talk about going direct to the FCC. How does that process work? How do you get in there?
So
Just FaceTime.
So the two parts of the question. One is ARDC. I want to mention them. They're a grant maker to us. They've made some amazing grants in the ham radio space on lots of really interesting stuff that is experimental. So there are organizations, powerful organizations in the ham world that are probably thinking closer to where you are. I don't understand all the politics to tell you, but I can tell you that. Again, you're really going to make me wrap the cabinet battle now, because politics are often personal, and you just have to get in there and do it. So that's the first point. The second point about the FCC thing, the magical thing about the FCC is that it actually doesn't really care to regulate. And that's been true under every administration that I've seen because I've lived through Republican and Democratic administrations. They don't want extra work. I'll give you a great example. So one of the classic things that we get told by people who violate the GPL is the FCC won't let us make this open source. Or so the licensed GPL says you have to. And we decided, well, you know what? Let's make our own wireless router. And so we made a wireless router. It's called the OpenWRT1. We sourced the hardware ourselves, and we built and released it. And it had to be, of course, FCC certified to be sold in the US. And we were nervous because we're like, well, this is 100% open source. They don't care one whit. For every single device you see, at least in the wireless space, that has an FCC cert on it, the FCC has never actually looked at it. They have a test firmware that they send around. It gets installed. The test firmware does a bunch of things. Test firmware passes. They say, oh, it's fine. Yeah, and you get the certification, and you just have to go to a licensed lab, which is not a government lab. It's a third-party, government contractor that just runs this test firmware on the thing. And what that says to me is the FCC gets the point that the hardware is what they're concerned about and what they're supposed to be regulating, not the software. And I think the whole mess we did with the FCC over SDRs and their whole dance over it was, you know what, we're gonna focus on what we know how to certify, which is hardware. We're gonna make sure that the hardware is not scary, and you can't do scary things with it. I'm sure if we had an antenna gigantic on that thing, they might have been like, oh, this doesn't pass something in that test firmware would not allow it. So I think the FCC is likely to leave experimentation alone, provided that you're using commercial off-the-shelf hardware and you can experiment with software responsibly. That would be my guess.
All right, we have a question over here.
Hi, thank you for all the work you do. That's really amazing. So, as a recent university student, I've been thinking about the space in general, and specifically in America, it seems like this is already well established in terms of how policy advocacy works and how open source as a whole is regulated. But internationally, and I feel like a lot of us here are not American-based, is there like a standard way to affect these government regulations, and how can we contribute as individual programmers?
Yeah, and I'm not familiar with spectrum regulation outside the U.S. It's been the only. I mean, I'm barely familiar with the U.S. It's very hard to follow just in one country. But as I was saying, revolutions are led by people who show up, and it's amazing to me if you still live in a democracy, which hopefully some of us do. The access to regulators is there, and education is really key. One of the things I think we did a really good job at in the early days of free software is, it doesn't run anymore, but there was this government and open source conference. And we would all go to DC every year, as in the early 2000s, and we had a guy at a university there who would just bring the policy wonks from all the agencies to talk to us, from all different agencies all over the world. And I think one of the big things you can do, if you can get people who are practitioners in free software, in amateur stuff, all that sort of thing, and get a conference, get an event where you can get the policy wonks to show up and talk to them, that makes a huge difference, because the people who actually make these decisions are the low-ranking people. The high-ranking people get a memo on their desk and they read the cover sheet and make a decision about the rulemaking. I mean, like I said, when I did this stuff with FCC, I never talked to a commissioner, but I know that some of the people I talked to wrote that language, because it's almost language that I kind of said, well, what if you said it this way? So those kind of things do happen. So I think getting the right people talking to each other is something you can do, and that's an organizing thing. It's just like organizing an event. in the, where the seat of government is.
Hi. You mentioned before about CD players, and I just wanted to ask you about, they used to have regional encoding, and it meant that you couldn't actually, like, it stopped you buying software in one location and using it in another location. And also if you bought like a CD player from a big name brand, they were the ones enforcing the regional encoding, whereas if you bought a Chinese brand, they didn't enforce it at all. So everyone was buying Chinese brand hardware, and all of the big companies lost out because no one would touch it. What are your comments on that?
Yeah, I mean, I think the bigger problem there is not that we're still in the DVD wars, that the regional encoding is a huge issue. I think that we've moved to this idea that people don't have the media of the stuff they're interested in anymore. And this is one of the saddest things about the huge win we had in HDTV, and now the media companies were able to bring DRM by forcing everything to be streaming, and literally reinserting the commercials back in, so you can't get past them. Whereas their big fear was we were not going to watch commercial. I remember years ago the head of the I think it was the MPAA said that if you go to the bathroom during a commercial break, you're stealing from the media companies. And so we moved to this world. I mean, I thought that was the big fight at the time, as you did, that like, oh, we have to make sure that these keys are cracked, and there was DECSS, which was illegal in the U.S., technically speaking, under the DMCA. So those were tough times, but I think the times we have now are kind of worse, because I think people have become accustomed to the idea that they don't control the signals they receive. It's under the control of the person sending it to them. That's my bigger worry than what you're raising at this point. Not to say that wasn't a huge battle and problem, but it seems small by comparison to what we face today, to me anyway.
Hello.
Okay, I think you're right in the light, I think. But
Oh, sorry about that.
You're there, it's fine.
Yeah, so I love open source software, and you make a great case for it. But what's the balance between, I mean, companies need to make money, right? And software is a great way to make money, intellectual property as well. So what's the balance between the open source world and the intellectual property where companies can actually make money, in your mind?
So years ago, I would have given a defense of capitalism. I don't defend capitalism anymore. I think that it is not the job of the technology to give a business model to anybody. It is certainly the case that people have made millions and even billions of dollars off of open source software. I mean, Red Hat being bought by IBM should be enough to show that. So I don't think that the business models aren't there. I do think that the handout that has been given to companies through the patent and copyright system is completely unreasonable. The amount of control that they're given and the right to monopolies, we were only supposed to have those. If you look back at the constitutional impetus for why we have a patent and copyright system in the US, it was to promote progress in science and the useful arts. So I turn that question back around and say, you show me how locking everything up is promoting science and the useful arts. If you can prove that to me, I'll say, okay, well, constitutionally, you really should be able to do that. But usually that's not the case. Usually, it's much easier so you can promote science and the useful arts by open sourcing things. You can watch my talks from like 20 years ago to hear me defend capitalism, and I used to, but I just refuse to defend capitalism now.
Hi. Some while ago, the FCC passed some regulations that you couldn't have a receiver that recovered roughly 800 to 900 megahertz, which was the cell phone band. Mm-hmm. And now we have SDRs, and they go from 60 meg to 6 gigahertz and more, and we can decode anything you want. And even if we don't do FM amps anymore, but we can decode an LTE cell signal. So the whole point is moot. What's the state of that regulation? I think it should be thrown out.
Well, and that's the interesting thing, is that the FCC is not interested in being a law enforcement agency, not really, right? Their job is to create an orderly spectrum that people can operate on and folks can communicate on. And the reason they have these rules is because they've given licenses for their spectrum to the LTE companies, and you're not supposed to be on them because then you're disrupting that. The interesting thing is that it's one of these things where the crime you're committing is probably has nothing to do with the FCC, right? If you're grabbing an LTE signal and decoding it, I am sure there's a dozen wiretapping laws you're probably breaking both in your state and federally. So what difference does it make if that regulation's there or not? Because you're breaking other laws anyway. And I think that's my guess of where the FCC is about this stuff. The FCC does not want and does not have the resources to check every piece of electronics that gets sold on the market in the US. They made this decision a long time ago that they weren't going to try to just keep people from getting SDRs, because that was, back in 2007, that was in discussion. There was this idea that SDRs should only be available to certain people. And if you got them, it was going to be criminal to possess them, and all the sorts of stuff were being talked about during that 2007 timeframe rulemaking. In the end, they basically said, well, you know what, we're not going to really regulate it as an SDR. And at least at the time, I don't know about the current numbers, they made this really convoluted process to get an SDR certified, and almost no one goes that route because they just go the regular old route in certifying hardware. So I actually think that it's one of these situations where you have a regulation on the books that is unlikely to be enforced, because if you were to break that regulation, you're probably committing some other crime. That would be my guess. But you're right at the sort of level of what my knowledge of the other FCC regs, other than the ones that I personally worked on as an advocate. So, but that's my best answer.
What most people don't realize is that it's perfectly legal, and it's in the statute somewhere, that you are allowed to receive any signal that you can get at. And Bob Cooper of satellite TV fame most famously put this to use when he put a dish in his backyard, and he said, I'm receiving the signals that are following into my backyard. So, and nobody could dispute that, because at the time there were no such regulations that you couldn't decode satellite signals. Nobody thought you could unless without professional budgets. But what is exactly what you're talking about is that you're not allowed to publicly disclose private communications that you receive. And we've got people receiving Inmarsat satellites and Iridium satellites to great delight, and they're just publicly disclosing it, and if nobody's going after them, then fine. That's the state of things. But publicly disclosing them is a little touchy, like the ADS-B transmissions of certain high-value individuals in their planes.
Yeah, and the DMCA is really the most sort of disgusting law in this space, right? Because if you teach anyone how to circumvent any copyright protection mechanism, that is a felony in the United States. So, for example, in the DTV example, you can receive that signal, but the digital satellite television signals, I'm sure, are encrypted. If you figure out a way to circumvent that encryption now, you are in violation of the DMCA. So, and I'm against the DMCA, since its inception. But this is another example where there are all these other regulations that are impacting the ability to do certain things in technology.
All right. Bradley, thank you very much. Thank you for coming and speaking to us and giving that history. And on behalf of the organizers here, we have a little, bag of goodies for you.
Thank you so much. Thank you.
You're welcome. And will you rap for us?
Do I really have to do it?
You don't have to. It's an
Oh my
invitation.
gosh. Okay.
So
So how many of you want to hear me do the Cabinet Battle 1 from Hamilton musical? Yeah. I would have done, the karaoke last night would have been a better venue, but So you insist?
I insist.
Okay, you insist.
Blame it on me. Yeah.
Okay, so I do all the parts, by the way, so I'll make it clear when I'm switching parts. Ladies and gentlemen, you could have been anywhere in the world tonight, but you're here with us in New York City. Are you ready for a cabinet meeting? The issue on the table, Secretary Hamilton's plan to assume states' debts and establish a national bank. Secretary Jefferson, you have the floor, sir. Life, liberty, and the pursuit of happiness. We fought for these ideals. We shouldn't settle for less. These are wise words, enterprising men quote them. Don't act surprised, you guys, because I wrote them. Oh, but Hamilton forgets his plan would have the government assume state debts. Now, you place your bets as to who that benefits. The very seat of government where Hamilton sits. If the shoe fits, wear it. If New York's in debt, why should Virginia bear it? Our debts are paid, I'm afraid. Don't tax the South, because we got it made in the shade. In Virginia, we plant seeds in the ground, we create. He just wants to move our money around. His financial plan is an outrageous demand, and it's too many damn pages for any man to understand. Stand with me in the land of the free. Pray to God we never see Hamilton's candidacy. Look, when Britain taxed our tea, we got real frisky. Imagine what's gonna happen when he tried to tax our whiskey. Thank you, Mr. Jefferson. Mr. Hamilton, your response, sir. Thomas, that was a real nice declaration. Welcome to the present, we're running a real nation. Would you like to join us, or just stay mellow, doing whatever the hell it is you do in Monticello? If we assume the debts, the union gets a new line of credit, a financial diuretic, how does he not get it? If we're aggressive and competitive, the union gets a boost, and he'd rather give it a sedative. And a civics lessons from a slaver. Hey neighbor, your debts are paid because you don't pay for labor. We plant seeds in the South, we create, yeah, keep ranting. We know who's really doing the planting. And another thing, Mr. Age of Enlightenment, to lecture me about the war, you didn't fight in it. You think I'm frightened of you, man? I almost died in a trench where you were off getting high with the French. Thomas Jefferson's always hesitant, reticent. With the president, there isn't a plane he hasn't jettisoned. And Madison, you mad as a Hannison, take your medicine. Damn, you, I'm worse than the national debt is it? Sitting there, useless as two shits. Turn around, bend over. I'll show you where my shoe fits. The reason I bothered to memorize that is because all politics are personal, and both sides are usually wrong.
Thank you again. Really great to have you here, and that I got to meet you in person after all these years. All right, next up is Marcus Mueller. We're going to give the maintainers report. And now, Marcus is a rare breed of human being here, in that he is a returning maintainer, a person who had the job for like as long as you have the job. For years.
For years.
And he stepped down, and then he is back with us in this role. And for those of you who don't understand what maintainers is actually like a technical word in the Free Software Foundation universe. And it's the person who's really, in one sense, the guardian of the code. There's lots of people participating, and then there's a person who's really the one that says, what goes in, what's not in, and has all those kind of conversations with people. So, Marcus, thank you. Let's hear all about what's happening.
Well, thanks. I will give the microphone. I've got
Oh, you got that one. All right, excellent.
So, yeah. This will be hard to follow up. So, there we go. That's not what I wanted. So, yeah, welcome to the maintainers update. We have been doing a lot of things since last year. So the outline of this talk will be mostly three things. First of all, I'm talking a bit about like the larger schemes of things. Then we'll go into how what's happening with Radio 4, because I actually think this is the slightly more pressing topic, and the more interesting as well. And finally, I will do the usual maintainers update thing where I talk about things that happen in what I've been doing the last year, or what the GNU 3 leadership has been doing with the code in the last year. So with that said, let's dive right in. A quick reminder, because as Eric said, I'm kind of back on the block. I've been away as a maintainer. I've been the maintainer from 2018 to 21, after which Jeff Long thankfully replaced me. And I've been around GNU Radio since around-ish 2009-ish, which is mostly Martin's fault, so hi Martin. As long as I'm not wearing my GNU Radio hat, I'm also earning money in some form as a consultant and as a contract developer. So these are the two hats, but while I'm here, I'm wearing the left hand hat, so don't you worry. So as promised, I said we start with the GNU Radio 4 topics. And what's up with this GNU Radio 4 talk, right? This has been making people a bit nervous since a long time, for no good reason, to be honest, because if you look around here, you notice that if anything, we're very aware that the strength of GNU Radio is a community that can stand together and actually get something developed together. So we will not drop users. We will try to use GNU Radio to actually, bring existing users forward and onboard more users. So when I say we believe it's the future, I actually do believe that. So we're not trying to make GNU Radio 3 be the thing that is out there forever. With that being said, we're also not killing GNU Radio 3 right away, right? It's not something that we drop on the floor and say, okay, today we're making the switch over. This will take a while. We will have that day where we say, okay, the official thing that we call GNU Radio is GNU Radio 4, but it's not there today. So as said, we intend to keep the community, and that also means we need to work on GNU Radio 3, because if this switchover is not instantaneous, well, we need to keep the thing attractive, to keep the ball rolling, to get people to actually be excited about GNU Radio 4 and invest time in porting it. So that is a kind of a conflicting goal, but I think we have a plan for how to do that. And that goal is that the plan is basically that we make GNU Radio 4 functionally attractive for a majority of users, right? That's how you do that. If we're doing that, then what's happening to GNU Radio 3? I said, like, the switchover will not, happen overnight. Like, we can't take multiple thousand users and force them to do something else. That's not how software works. That's not how open source works, especially. But there is the need to assist them in going into the new direction. So we need to find ways, and there's development effort that needs to come out of the community to make it easy to port our existing ecosystem of out of 3 modules into this new framework, right? Currently, we don't have good Python bindings, for example. So that's something that we need to work on, because there's a lot of existing code base that's actually Python-based, right? And telling someone to port something to a completely different C++ framework is one thing. Telling someone to learn C++ and then port their Python blocks, that's not going to happen, right? They did. It's unlikely to happen in most cases. We need to, for GNU Radio 4 to take off, we also need to tackle the installation problems. And everyone who's been around with GNU Radio 3 for a while knows that this has already been hard for us. It took like a decade, maybe 2, to actually get where we can sincerely say that we believe it's not hard to install, and we're still working on that. I'll be addressing that in the GNU Radio 3 context a bit later. And the final thing that I'd like to see, and also have concrete ideas on how to tackle that, is that we make the transition easier for active developers. So if you're now developing something interesting, say you have a satellite TV receiver, something that you want to have, and now you're considering, will I write that for GNU 3 and get like this huge user base that I'm addressing, or will I write it for GNU Radio 4 and get this like large user base in the next 50 years that will hopefully be using GNU Radio, definitely, but then GNU Radio 4 and the successors to that, you would be in a conflicting situation. So by making it easier mentally to take your code and make it portable, we hope to actually make this happen more smoothly. If you've been following the GNU Radio 4 development or been sitting in Josh's Write Your First Blog session, then you know that it's not trivial because the API is different. But a lot of the concepts, like this is a block, you connect it, there is a function that takes your samples and processes it. It's so similar that if you take away a lot of the crafty, boilerplatey, just repeat these things away and make it more clean and say, okay, this is a preferable way to do things, here's guidance, we can actually make this easier, this transition. So transitioning to GNU Radio 4 will become easier if we make GNU Radio 3 better in some ways. That again, still means that we have to, assign our resources. This is a completely volunteer-driven project, so it's not like I have like 5 full-time engineers that I can say, okay, you do this and you do this, and then next week we have a sprint meeting and agree on what's been done. The things that we need to do in which order is kind of A, negotiable, and B, it needs prioritization because we can't do all the things at once. Simply because there's not enough, Johns to go around, and and then also like we've been super reliant, and it's been awesome on Ralph's team in Germany, and they gave us the code in hopes that we will, and this is the agreement, that we will make a community project out of it, where we make sure that, okay, someone wrote that code base, they gave it to us, they offered to license it in a way that they can work with, that we can work with, and that's, I mean, Bradley touched on that, that's actually been a discussion, right? We've been haggling with that a lot. And that's been awesome, but it also means that we now need to actually put in our work to define the things that will be important for the community. And if you ask me, and kind of in a lucky position to have the stage right now, there's a couple of main topics there. So the user experience of GNU Radio 4 is awesome. It really is if you care about speed. You get a massive speed up for most operations because it's not doing a lot of the buffer handling, the cache invalidation that GNU Radio 3 comes with kind of invariably. But then again, a lot of our users are doing something like, I want to decode a DSB message. These are like a couple kilohertz wide, if at all. And you can do that on a Raspberry Pi today relatively comfortably. So maybe they don't care as much about speed as about ease of development, for example, or as about ease of installation especially. So there's some angle that we can build upon, right? We don't have to care about improving performance right now. This is actually also already awesome enough. But we have to work on the user experience for especially like the less involved, less technical user. Then on the developer experience, there's been like last year's European Radio Days in Darmstadt, and these were super interesting, and we identified, Eric was there, he's still happy about that. So that was very impressive, and the things that had happened since then are also very impressive in the sense that if you go there and you compile a block that happens in seconds, right, or fractions of a second, this is now very easy. You don't need a lot of RAM. It's actually a very nice to use software, and you can very well develop for that. The other nice thing is that, if you've been dealing with GNU Radio scheduling, I don't want to say scheduler because, well, there's no scheduler. We just tell the operating system that this block might be ready to work. Maybe you call it, maybe you don't. There's a lot of corner cases that come with that. And a lot of these architectural things that have grown over 20 years of history, they are not there in GNU Radio 4, right? This is a clean slate approach. You can actually avoid a lot of pitfalls if you know about them beforehand and think about them. So while I'm pretty sure there will be enough corner cases that we will, which we are yet have the fun to discover, this is already a pretty clean slate. So from a developer perspective, if you're not mentally invested in the GNU 3 code base, right? If you're not feeling this loss of I'm familiar with all of this, that's super nice actually. And it also comes with, and this ties back into what I've been saying about the transition out of tree module development, the minimum set of files that you need to handle to know what their purpose is. For some block in GNU Radio 4 is rather small. So because GNU Radio 4 has this idea that everything has a single source of truth. It's not like we have this header that defines the public API, then we have this other header that defines the implementation's internal API, then we have this other file that implements that, then we have this other file that implements the Python bindings, and then we finally have this other file that defines the block that appears in GRC. This becomes much slimmer, right? This becomes much more tractable. There might be still, if you're new, some magical words in there that you just, first of all, start to accept, and then I'm having the same problem as Bradley had lately. I should just publish that password at some point. It's much nicer to develop, and that's actually something that, like, I saw that and was like, oh, we should maybe have something similar in GNU Radio 3. So what's not quite there yet, but again, big progress, the block library, right? There's a lot of core functionality that's definitely 100% there, right? We have all the converters that you could dream of, all the math operations that you usually will use. There's filters in there. I even type them correctly. Usually I write fiddlers, and that's kind of an unlucky conversion. So all the core functionality is there, but we will need to work on things like digital comms, prototypes, like the things that you do, the high-level functionality that you use when you're more from a communications background and less from I need to make this very useful for physicists doing experiments. That's kind of the community's job to actually come up with. And again, this is a great chance to do things that are cleaner. Everyone who's worked with grFEC, it has some really cool blocks, but the API is all over the place. The bugs, they're all over the place, right? The performance, it's not all over the place, but it's definitely not consistent. Same for digital blocks, right? We have constellations that are not normalized in power. Others are. This is interesting for someone who uses that and then publishes a paper and says, comparing these two, I saw this exciting thing, and then you're like, yes, that exciting thing is a bug. So this is going to be something that we have to do. So the other thing that I think that is very central to developing a reasonable user base is to have visual blocks. Like we have in GNU Radio 3, we have all the Qt GUI things where you can have something that looks like an oscilloscope. You can have something that kind of looks like a spectrum analyzer, right? GSI has something like that for their internal purposes, and it's open source, you can use it, but it also comes with their use case. It's tied a bit into the way they think about what am I visualizing, what is the purpose of this application, and I think there might be some input where we differ, where the communications engineer, we is in this case, the old school GNU Radio guys, where we kind of want to see different approaches, and that's something that we need to write. So I've got they have a very nice image UI-based framework, and I want to go in that direction as well. Someone around the framework that I differ. But as said, we're on super friendly terms with them. We're going to definitely steal some of the code, use it to our own advantage, and that's the power of open source, right? So let's do that. On the GNU Radio 4 API, I'd say it's basically stabilized, right? You know how that block will look like. There's not going to be a big surprise anymore. So if you start writing a GNU Radio 4 application today, it's very unlikely that aside from minor tweaks, up until the release of 4.0, you will need to rewrite a significant amount of code. As mentioned, we're only C++ so far. this puts a bound on who's going to adopt this. We have a very nice declarative way of defining flow graphs, which is much like this feels very good because most flow graphs as a setup are mostly static, and then you want to change things maybe at runtime. That is fine, but in a lot of ways, writing code that defines these are the 200 blocks, and they're now I call connect block 1 to block 2 is not as elegant as saying I have this definition of a graph. In that sense, through that declarative interface and through the self-describing blocks, it should be fairly easy. And this comes always with a big asterisk. And if you ever sat in any meetings where someone said that, you know this is a lie. But it should be fairly easy to write a Python binding and come up with reasonable RPC. And why that's important, I'm going to go into, I think, on the next slide. Yes. A design tool. GNU Radio 3 has the GNU Radio Companion, right? And if you're familiar with that, it's I should have put a screenshot here, but if you're familiar with that, that's a rectangular box where you can draw flow graphs on. So you pull in your nodes, you connect them. It's written in Python. It used to be written in PyGTK as the graphical framework. Hakon has stepped up and finished the work that Seth and others have started on the Qt GRC. And that actually works. So, by the way, if you're today using a modern GNU Radio 3, you should be trying to use the Qt GRC because it's actually useful, it's prettier, it's faster, it's less buggy. But it's also, it has new bugs, right? And I don't find them all personally because we can't click on everything in every order. But you know, a room full of crazy developers can. So please do report bugs in GRC Qt. But we don't have that for GR4. Again, this is a situation where GSI themselves, they have a very mature and actually very useful thing, but it ties into their use case again. And that might really not reflect very well what the user needs. We've come up with a plan that actually to rewrite, or not rewrite, to implement a design toolkit in the browser. Why in the browser? Why on earth would you do that to you? You're a room full of C++ and Python developers. Why would you want to do something in the browser, right? There's JavaScript there. That's actually been super often requested feature to be able to design a flow graph, a show flow graph in the browser, both from like the educational settings, right, where I can stand in front of a room full of people with a laptop and say, if you want to design a GNU Radio flow graph, let's not talk about where it runs, but if you design it, you can just go to this URL and you start designing a flow graph, you can upload it, whatever. That would be very useful to have in a school setting, right? Where it's not an option that we spend the first half hour installing stuff and figuring out the peculiarities of everyone's systems. The other thing is, we've been having, like I had to look this up, Josh Bloom wrote this a little more than 18 years ago. And honestly, thank you, Josh. But it also shows we're pretty good C++ and pretty okay Python developers, but we're kind of so-and-so-ish GUI developers. We're kind of behind the curve on that, right? We can read books, but we're never really the people to write great UX. And the other thing that it turned out that the approach that someone 19 years ago would have taken writing a graphical toolkit in Python would be you write code, and that code defines, okay, here's a window, and there's a button, and that button gets an event listener, and blah, blah, blah. And it's a very inefficient way, because you get spaghetti code, and you get code that no designer can work with. The designer always needs a developer to do anything. And that precludes a lot of people. And the other thing is, it's really hard to find DSP experts. It's nearly impossible to find DSP experts that will, in their free time or for company money, design graphical toolkits, because that's kind of the opposite of what they're used to doing. And it's a very different mindset. So we're hoping to, we don't have this home advantage. We know this language. It's easy to code. No, guys. programming is not the hard thing. Knowing to do what to program is the hard thing. That's my kind of, if you've been around in a couple of last years, this is my gripe with LLMs. It's not, the hard thing is not writing the code. The hard thing is knowing what code you want to write and what that code should be doing. So, and we're missing that. Like, we know how to write C++, we don't know how to write a good GUI, and that's the problem. So we're trying to tap into actually a larger pool of people that know how to do that, that would maybe need help doing DSP stuff, but actually you don't need to know anything about DSP to write a good GRC, right? We can tell them, like, this is an application that, like, this is how it looks. We already have good examples of large flow graphs, right? There's a reason why we have milliband in, like, GRC3. We can show, okay, you need to make this useful, and we can, this is possible. The other way is hard, right? Teaching these P guys is not trivial. What that requires, though, is we have something running in a browser, and browsers are constrained environments. They're usually not allowed to just call some native library, right? They're not allowed to call the GNU Radio runtime. You can run a GNU Radio 4 runtime in the browser. That's what GSI does. But it's not the same as running it on your computer or on some remote Raspberry Pi, right? So how do you do that? You have some runtime on a remote system or on a local system, and you only have a browser interface. Well, you get some RPC, remote procedure call framework. And in this case of browsers, that's going to be an HTTP REST interface. But we need to implement that endpoint, right? GR4 has explicit RPC-friendly interfaces, but they don't talk JSON over HTTP, so we need to work on that. Yeah. So I might actually skip this slide mostly because it's just highlighting, and I've been doing so many advertisements for GR4 now that it feels a bit duplicate, but the developer experience of GR4 has come a long way. It's really, really nice now to work with. The directory structure, if you ever wondered, is GR signal source now in GR blocks, or is it in GR analog, or is it might be in GR filter, because kinda. It is in GR analog, and it makes no sense. And that's not a problem for GR4 because it's a clean slate rewrite, and we could never change that in GR3 without breaking all applications. So this is another advantage of writing it clean slate. We will, it has a very clean directory structure. We need that clean directory structure because, as mentioned, right, different license for the core than for what ported blocks will have, because ported blocks will, that is kind of obvious, they're derivative works of GPL-v3 work, so they have to be GPL-v3 or later, in our case. So we will have blocks that should not be contaminated, or no matter how you look at it, be contaminated by MIT code or contaminating MIT code. So we need this clean structure. So that's actually kind of nice. If you work with GNU Radio for the first time and you're an old school C++ developer, you look at it and say, okay, this is a bit much template magic, maybe. But as soon as you gotten used to that, it's actually much nicer. You don't need to remember, like, this is a typical structure, that's a convention. It's actually like the type system enforces things, that's nice. And I've been highlighting this earlier. There's a single source of truth theory where you say, okay, the block itself tells you what the block itself does, right? And that avoids you running into the problem that we're currently solving in GNU Radio 3 with hashes that control whether your Python bindings match your header. Right? This is definitely a workaround. This actually just says, okay, I have these functions. You can interface with these functions, and let's go with that. Like, this is the right thing to do if you can. Back in the day, we couldn't, right? To just bind something in C++ without reflection doesn't work. But GSI made it work with reflection, so might as well. That ends the GR4 part of my talk. And I'd like to take a step back, but also kind of a step forward into what I can actually tell you what we're doing. So Josh mentioned that Jeff Long as a long-term maintainer stepped back earlier this year, so he volunteered. And I wrote a small blog post that explains all that, and I'm super thankful for Jeff for having done this for so many years. So it's incredibly hard to achieve Jeff's consistency when it comes to backporting commits from the main branch into our maintenance branch, where we released the 310 series from. So I'm actually struggling with that. So this highlights how much of an asset Jeff Long's contributions were there. So I'd actually like to formally thank Jeff here and give him a round of applause. I hope he's watching the stream these days. Yeah, and the only way I can actually pay him back is by, achieving his quality over time. And that's, as said, that's been harsh on me, actually. Why? Because we have, due to this activity in backporting, it was very attractive to contribute to GNU Radio, right? Because, you write a patch, and it's going to appear in a minor release in a couple of weeks to months. I've not been keeping up with the release speed. I need to do a 310 release soonish. But that also means we have higher load on people opening pull requests, higher load on people that need advice on how to write something, right? More people that actually report bugs, which is awesome, right? Nobody would doubt that. But it also means you lose oversight of all the components. And what we've been coming up with is that, well, we're large enough to actually need subsystem maintainers. And we've been actually more or less officially doing that for the GRU UHD component, which makes a lot of sense because, UHD gets only used by one type of people. That's people with years apiece. So Martin has actually been maintaining that subsystem. Thanks, Martin. The GRC that kind of evolved that way is these days maintained by Håkon. And the GRIIO, so the framework you'd be using if you're interfacing with a Pluto SDR or if you're running on an FPGA evaluation board with FMC cards that directly talk to analog devices converters, that's Henning Paul has stepped up, and I'm super thankful because that was actually a harsh, a big step, because he was the first one that we actually just pulled in and said, hey, you've been working with IAO devices, you seem fairly reasonable. We can't offer you anything. We can only offer you advice if too many people ask too many questions. And he's just been stepping up. I don't think it's been super much work, to be honest. But it's still, I'm super thankful that someone took that leap and tried to be a subsystem maintainer for us. So I need more of these. So if you feel like, oh, I'm definitely, I've been doing a lot of convolutions lately, I would want to look at the GR filter submodule, please step up to me. Or that's the same for the DTV and whatever, right? We have more submodules than in Intri than we have maintainers, and we need to change that. What we've been working on code-wise since the last 3.10.12.0 release, if I'm not mistaken, is mostly GRC Qt. So there's been a huge amount of bug fixes with that. So if you've got a very recent installation of GNU Radio 3.10, you can just launch GNU Radio Companion with the --Qt, and you get the current UI. And most people don't know that because we've been conservative about breaking people's workflows, right? So the default still is GTK, but you can explicitly say, hey, I'd like to start a Qt variant, and you get that, right? And do please try that out. An exciting thing that's come out of that work is the ability to have the workflows. And the GRC workflows enable a developer to say, okay, instead of generating what we know as the Python generation, the default thing where you get a Python file that you can execute, or the C++ generation, which I don't even know how many people are aware. Let's actually ask here, who knows that GNU Radio Companion can and could for a couple of years generate C++ flow graphs. And that's about 1/4. You always say it's about 1/4 or 1/3, if that's the question, by the way. So that's about, it was a couple of hands. So you can, if you're aiming for something that doesn't have Python, if you want to compile it to be more compact and not require Python, you can today, most blocks in your flow graph just generate a C++ flow graph instead of a Python flow graph. It comes with a directory, with CMake infrastructure and everything. Again, it's a bit more than you would want to have, if you're perfectly honest, but it works, right? So, and the GRC workflows take this idea one step further and say, okay, you can also define your own workflows. So if you have blocks that need FPGA image generation, and that's basically where it comes from, right? Being more flexible about accelerators in SDR devices featuring FPGAs. So you can write your own frameworks there. So this is a really important feature because it also means, okay, we're getting better at this heterogeneous thing that we've been talking about for years. And I've been on that slide for too long. And let's, yeah. So let us talk about work that's not been released yet. So we went out and actually paid a kitware consultant to unfudge our CMake in a way, right? And that work is not currently in tree, but it's the basis of National Instruments work to make make good installers for current UHD and GNU radio. So the situation is this: if you buy a new UHD device and you want to, say, use like the newest and shiniest RF NOC, you'd be liable to install UHD yourself. But then you have a GNU radio that's built against the old UHD, so you need to rebuild your own GNU radio. And nobody wants to build software from source unless they're a bit, I mean, I don't blame people, but it's not something that I would want to put on most users because they mostly want to use software, not to build that. So that's been a high step for a lot of USOP users, and so it's only logical that National Instruments has a natural interest in making that more smooth, and they've been stepping up, and I'm very thankful for this, at providing installers for both combined, so you can have a recent version of UHD and a GNU radio version, and everything works together. So, but that actually requires work, and I'd like to give a shout out to Marion, who's in the back. Please be nice to him. He's got to work with Windows, with Linux, and with CMake and all installers and all at the same time. And he's still a nice guy. I would be super grumpy. So please be nice to him and also ask questions. There will be some announcement in the rather near future where we actually need people to test this, and please do engage with that. But these things, they change CMake in ways that change where things get installed and whatnot. So this is going to be a breaking change. We can't do that on 3.10. We have a formal document that says if we're not increasing that version number, that 10, then these things do not happen. So we need to release 3.11 to incorporate that. So that's not too far in the future. The other thing that needs to happen very soon is the Qt5 to Qt6 migration. So everyone who's been around knows like Qt has a new major version every couple years, so basically once a decade. And it's about time again. Qt 4 to 5 was kind of has to happen overnight very quickly because we're falling out of Debian support, and I mean, thanks mate. But I was really, really nervous about that because we started that, and then it got stuck at some complicated points, and then we realized it's requiring CMake work that can kind of conflict with the CMake overhaul, and things get conflicting very quickly. And but what did not happen is that the newest Debian released without a Qt5, so we're good for another while, but it's not something that we can sleep on, right? We need to still do that very soon. Also because we kind of want a few of these features. But then I'm not sure whether we can do this. It's not clear to me whether we can do this without breaking changes. So this happens within 3.11 or will need 3.12. So might be 2 minor releases within a year, but mostly without too much user breakage. So what's the things that need to happen kind of at some point are, the usual. So please, everyone pick one of these. We'll meet after lunch and we get these sorted out. No, we've got enough bugs to make you shiver. Like we have one mutex that logs your block's buffer, right? Or buffers that it writes into. And that mutex logs reading the read pointer position, writing the read pointer position, reading text, writing text, message passing, name changes, whatever. And there's no need to exclude readers from each other. You can read the same value as many times from as many CPU cores as you want, as long as you're not changing that, right? But this leads to locking congestion. And it's not only a performance problem, it actually stops me from doing things that I wanted to do for a customer of mine. Namely, I wanted to have something where I can call a wrap Python function from a block context, right, from a buffer context that would inspect something and say, yes, that works. And I can't do that because Python holds a lock, the buffer holds a lock, can't release that one while that's active, and we've got a deadlock. So I need to sort that out. Well, we need to sort this out. The other thing that's been around for years is that in our Qt GUI visualizations, we are exchanging data across thread boundaries in ways that Qt is not compatible with. That mostly goes okay, because that data does not very often get changed, and it's not very often getting read. But you can definitely crash a flow graph by having a slider in your GRC that adjusts something in your visualization and you slide it fast enough. And if you can make something crash by sliding something fast enough, that's not good. So we need to fix that. We urgently need to fix that, actually. So the other thing is, like, also a lot of you might be aware of the Qt visualizations not being perfect. And what not being perfect is like the waterfall sync has not uniform height and that's confusing to me. And if I look at some chirp that should be linear and the chirp has steps, I get nervous. But then it turns out my signal processing is fine and everything is good. So we need to maybe actually re-implement some of this and need to decide whether we fix the threading issues or replace the thing. But that would be a big step. And I don't want to take that big step while we're investing a lot of resources, like while we're taking away resources from perfecting GR4 to a point where we can mass adopt that. So that's an interesting, that's an actually contested resource there. We need to fix the threading issues. There's actually non-negotiable. We actually need to fix the waterfall sync. It's actually also non-negotiable. But I don't know whether we can actually come up with a visualization that fits like GR4 and GR3 without a lot of code duplication. That would be nice. And there's a lot of easy to fix, in theory, long-standing bugs, like if you use an AGC, you know what I'm talking about. Which one? Yes, all of 3 of them. What are the difference between the AGCs? I don't know. Nobody does. So we need to figure that one out. But as I said, there's enough bugs that need to be fixed in the near future. GNU 3 is not done. It will continue to be maintained. And it will continue to improve with the purpose of keeping this community very much alive, very much making it possible for people to develop very useful applications that will also then enrich the same community from which we basically recruit the people that will be adopting GNU 4, right? So this is, again, I believe GNU 4 is the future. That does mean I believe I need to maintain GNU 3 to a degree that makes everyone happy. So that's my takeaway there. So looking a bit into, if you had too much time, what would you see like to write in your near future? I mentioned this feature where I wanted to be able to do some Python from within the buffer handling. And that came from the situation that if you currently know how to handle a stream text, or this is going to be a bit technical, if you're not into the source code development with GNU Radio, doze off, you get 5 minutes. If you're writing a GNU Radio blog and you want to handle texts, right, what you do is you generate a static vector of tag. You pass that vector by reference into a get text and range function. That get text and range function copies over text into that vector. Then you go and say, I only needed the first one, but thank you. Then you check the first one, has it the right key? Oh no. Then you advance to the next call. You get all the text copied over, you ignore all of them after checking that they are not what you wanted, and this is incredibly ineffective. This is actually one of the things that if you may benchmark an application that does a lot of things with text because it's, for example, correlation for a preamble that you're looking for. And you have some block that tags, like I saw this preamble here, or at least I saw a peak that might be a preamble here. Here's its amplitude, here's its phase. That's usually very work intense. So I thought it would be nicer to actually be able to have like, apply this to all the text and range. And if something works, please apply this function. So I came up with a function called apply text to text and range that does just either call a function on all the text and range or takes another, I didn't put that on the slide, a predicate function that either returns true or false on a tag, and only if it's true you do something on it, right? That's a very usual kind of slightly functional way of thinking how you do work with a vector of something that you're not controlling. And in the consequence, if you're into modern C++, something with ranges where I just take tags, pipe them through some filter, pipe them to some transformation, pipe them to, please put this to the output. That's what could come out of this. But I couldn't do that because if I do this for C++, I want to do this also for Python because it's no good if you're developer in one and then you say, oh, I only need a small block that I could write in Python, and then the function that you would need to do is missing. So I couldn't do that with Python because as soon as I do that, I deadlock. Then I mentioned that GNU Radio 4 has cleaner block structure, and we can go there. We cannot achieve that, and it's not going to be desirable to achieve that within GNU Radio 3, but we've been doing this dimple-imple thing where I have this block that only has the very important public interface that is nice for keeping your SO clean of objects or of symbols that you don't want to have in there. Very awesome. Modern compilers have visibility. It's not that important anymore, right? And to an out-of-tree module developer, they're mostly, let's say, leaf nodes in a library dependency chain, so they don't care really about what they expose, right? They are not profiting as much from I have an impl and I have the plain block. So that's 3 more files that they could do without. And the other thing that I really, really liked is how GR4 blocks are self-describing. We will not get there. We don't have the C++ versions to have the reflection. And that's also something where I'd actually say, oh, it might be a nice feature to convince people to go over to GR4, on the trade of how much work would I need to put in to make that happen versus how attractive is it to motivate people. But we can do something like, hey, can you describe yourself well enough so that GRC could write that, draw your block, right? And that should be happening. If that also allows for us to get rid of the separate pybind file, that would be very nice, right? But on the other hand, I don't want to clutter your implementation class with like 15,000 lines of pybind, please .wrap this function. This is the default argument. This is the default argument B. This is the default argument C. That's not something that you want to see in the code where you have 5 lines of signal processing and then 100 lines of Python wrapping. So that's something we need to experiment with. So this takes a lower precedence in my priority list. And I'm very happy that yesterday I learned there's actually going to be a talk because I've been terrible at preparing for conferences. There's going to be a talk about latency bounded processing, and it's awesome that I had some latency typing in my computer to the point that things got too late and it got locked out. At low sample rates, say you're implementing a voice modem, right? Radio is not that useful because it tends to try to fill up a complete buffer, right? That's a bit of the streaming architecture. Is you produce as much as you can, and if your one end is very quick at producing samples because an SDR and the other one is very slow because it's the output of some voice codec, then there might be a lot of latency because a lot of buffers on the voice side have a lot of space for samples. And we need to bound that to be useful in that space. That is some problem that GR4's default scheduler does not have, right? And there's only one right now, so GR4 does not have. But it's something that we still need in GR3. And getting us back into that space where easy voice comms are a thing that you reasonably implement within radio, and not only like a toy example where you have an FM modulator, DM modulator, but something with packets. That would be very nice to have. But again, like if time permits. So that kind of brings me to the end of my talk, and I think I'm run over of time. Well, we're kind of okay. Okay, so that means I'm asking for questions. Thank you very much for your attention.
Questions for Marcus?
Can you check the chat for questions?
Hi, yeah. Is there any work being done for GR4 in avoiding the whole UHD issue with...
Which issue?
Like the versioning issue where you want the newest UHD and having to rebuild the whole thing?
So this is mostly no, because that's mostly a release management issue, and we haven't done the first release of GR4. The trick with that is usually that the library you're consuming needs to be stable in its API. And luckily, UHD has been evolving quickly to support new features. And when that comes with an API breach, then we basically can't do anything about that. We would need to have some shim library, which is performance-wise also not ideal. So I guess for the UHD side of things, there's no better way to say than if you need a binary incompatibly newer version of UHD, you will need to rebuild whatever software uses that. But again, like GR4 is by now very nice to build, and it has a very clean API, so that makes a lot of things easier on that end. But it's not something that the source code itself can solve. But thanks for the question.
Any other questions from Marcus?
Thank you, Marcus.
You're welcome.
Feel free to corner him at any point out in the hallway and ask those other questions or whatever there might be. So should we just go on then with Mark? Are you ready? Or early break, but is there stuff out there? So should we do Mark and followed by a longer break? Or?
So we'll go ahead and make a break for an early break, just because I just moved Mark on the schedule to an opening, so we've got him slated for after lunch. We also have, for those here, other lightning talks that have opened up for this afternoon and for later today. And when we get back from our break, we'll actually have our fireside chat with Matt and Eric, if you join us. So yeah, early break. Not sure if the food's there, but I believe, the food is there, so we are good. All right, folks, thanks.
I'm glad you're here. My name is Derek Kozel. I've been up on the stage once before, but I'm one of the GNU Radio leads. But something that I hope I've shared with a bunch of people, but not everyone broadly, is that my first presence here at the GNU Radio conference was as a student. During my master's, I did a project on using evolutionary algorithms to try and adapt digital constellations to channels, and I ended up using GNU Radio. Quite poorly, as it turns out, missing some of the basics of digital communications understandings on synchronization. I was one of those students who sat in the GNU Radio chat and ended up asking questions and had people, not Marcus Miller at the time, but similar people from this wonderful community answering questions which to them must have seemed a bit like, is the sky blue and why? And so coming to the conference, that was about 2012 or so, and I've been able to be part of the community ever since then. And a couple of the people who have been there the entire time and popped back into the community a little more recently than that are Matt Edis and Eric Blossom. And so I'm tremendously grateful to welcome them up and be able to be the host of this fireside chat. And so if you please want to join us, these are people who probably need no introduction to the community, but we're going to try and get to know them a little bit better and have them answer some of your questions, both that are pre-prepared and perhaps we'll have a chance to solicit something from the audience in the meanwhile. But I think that the duration of the project is one where it's great to be able to bring up pieces of both the history of the project and perspectives from the beginning all the way through to the current day. So I see that you've already included that in your questions, which makes my job very easy. So if we could start with just a basic introduction of who you are and how you got involved with the project. I think that's been started already today, but let's keep this as an enclosed conversation, given that this will end up on YouTube and somebody won't have the context one day.
I guess the shortest version I can think of is how I got involved was I was interested in two things, one of which was there were some early digital cellular standards in the US that had a problem, which was that the cryptography in them was like poor. And I wanted to make a point about, I should just be able to like pull those bits out of the air and demonstrate that that cryptography was like really poor, like linear, like a very funny kind of cryptography. And I could have like rented a piece of test equipment and just solved the problem that way, but I was like, well, what's the fun of that? And I also wanted to teach myself about digital communications. And I didn't really want to like go back to school and things like that. And so I'm like, talked with a friend. They proposed, why don't you create a free software project to go write that software that you want to be able to use? And it started really there. That's the very abbreviated version. But that's kind of how it got started.
If it works, yep.
Okay. Yeah, so I had been a ham since I was a kid and had been, interested in radio technology for a long time, and I did my master's research on wireless networking, and when I went to actually a ham conference to present about some of that work, I heard Dwayne Hendricks, who actually recently passed away, he gave a talk about software-defined radio. And I had actually never heard of that before. And to be honest, my first thought was, well, okay, that seems sort of obvious, like you can do anything in software. Why are you making such a big deal out of that? But later I sort of saw the power of that concept. And this was like 97 or so. But then while I was working at a Bluetooth chip company in the very early days of Bluetooth, I used a free software sort of wireless system simulator called Gossip that was very short-lived, but was interested in SDR, but didn't, you know, sort of like start doing anything with it. And then there used to be a website called freshmeat.net, which was like just like people would announce new software projects there, and it was sort of like before there was, I don't know, Hacker News or any of that sort of stuff. And I guess you must have submitted GNU Radio to that, and I saw, oh, radio, that sounds interesting, and so I joined the mailing list, and I guess that was late 2000, early 2001.
Yeah.
And so that's how I first saw GNU Radio, and you know, it's like, oh, this looks pretty good. This is a pretty powerful idea, and just sort of, you know, but we never really had any interesting hardware to work with. But Eric had, I guess you sort of saw that I was getting involved, and then we. Or John Gilmore and EFF were funding you, and you were like, hey, you know, you look like you're doing something with this. You want a computer and an A to D card, and we can do some interesting stuff with it. And that's sort of where it really took off, I guess. And a lot of my interest was, you know, sort of using, you know, sort of using software radio to do, you know, ham radio stuff, but other things as well, and experimenting stuff. But there really wasn't interesting hardware, and that's sort of why I ended up, you know, eventually ended up building USRP. But that took a while to get there.
Okay, I think we're going to do a mic swap for you, maybe.
I want to point to just something right now, is that we were able to find off-the-shelf hardware, this A to D board built by Measurement Computing, then was acquired by National Instruments in kind of a weird circular universe. But that board cost more than the PC we were using to run it on. And that was just kind of like, we're not going to have a whole lot of people come play with us if you got to go, you know, for this one board to enable the thing, you know, to have to spend like, oh, you know, another, you know, 150% on your budget just to get in the game.
Yeah, and you still needed RF conversion in front of it. It was really just a data acquisition and all that. So yeah, I mean, if I should get into the I guess the next question, but yeah.
Yeah, so this is an audience-solicited question, and it does flow quite nicely. So what was the first application that you made involving a usurp? You know, what did you have in mind when you were drawing the specifications, and then what did you actually use it for?
Yeah, well, so I mean, we were using GNU Radio, and like we heard earlier today, there was the big application was the HDTV decoder, and that was sort of like our Mount Everest, right? And it was, you know, by making that work, we sort of flushed out all of the different things that GNU Radio needed and didn't have, and so it was a great, you know, North Star for the development. But the whole time, you know, we had this, you know, this measurement computing card, which was just an A to D converter, and it was like it was a PCI Express, or I think it was just PCI. Yeah, it was, and then a cable modem down converter board. Like it was like one of those metal can down converters that you would find on the back of a TV, and it, you know, you had an F connector instead of an SMA, and and you found like the one that down converted low enough it could go into this A to D converter board, and I was like, you know, this isn't practical. It was like it was that or sound cards, and there was nothing else, and so. You know, I was like, well, this is, you know, there's FPGAs, there's nice A to D converters, there's, you know, USB 2 is a new thing, and there's some decent data rate there, and so I sort of drew up a block diagram of you know, what I thought was an ideal SDR, which had like, you know, RF converters with you know, amps and stuff, and then A to Ds and D to As, and a FPGA and a USB interface, and I you know, I would go to conferences and talk about, I was like, somebody's got to build this. Like we were working on GNU Radio. I was like, somebody really needs to build this. This would be awesome. I just want to use it. And nobody was doing that. And so eventually, we just started doing it. Yeah.
Yeah, we did. There were a few people out there building hardware that kind of met those requirements, except they cost like at least 10x or 20x what we wanted to pay.
Yeah. Everything was in the tens of thousands of dollars, and it was, sort of intended for military or defense purposes, or big, sort of commercial test equipment kind of thing. And so the price wasn't compatible with the amateur or the hobby kind of model. And so I just went around trying to convince somebody to build this. I probably for a year and a half or something. Eventually, it's like I guess I got to do that. Really not because I wanted to. I was not looking to make a company out of it. I just wanted to use it, and nobody was making it. So I built it, and Eric wrote the drivers and stuff, and then but I still didn't think there would be a market for it. So we were like, John Gilmore found us this deal with University of Utah where they had some NSF money, and we would support that, support the software, support the hardware, and then the university would somehow build and sell these things. And after a while, it was clear the universities aren't set up to do that. And I sort of reluctantly, so just for time, for sort of chronological, I guess it was like 2003 that I started, actually sort of designing the hardware, and, found a couple of people on the mailing list who were sort of interested in helping, and that didn't really work out. But, and then in 2004, we found this NSF money, and then that, it was clear that they weren't really able to sell this, and so, but people on the mailing list were like, hey, I want to buy this. And I was like, okay, I guess so I was really afraid, like the first time I bought, so I guess this was like late 04. So 2004, in August, I quit my day job, because at this point we had the NSF money from Utah, and I was like, okay, I'll be able to pay the mortgage. And I quit the day job, started Edis Research, and then built the first batch of 100, like basically after I had pre-orders for most of them. And I was like, oh my God, I'm gonna have 30 left over that I'm not gonna be able to sell. I bought like 100 at a time, and just people kept ordering them and started shipping them January of 05. A few beta people before that, but yeah.
So there was a global market for more than 100 SDRs.
Yeah. Yes. Yeah. And actually, speaking of global, the first order I received because of like time differences and stuff was from South Korea for 5 units, and I was deathly afraid of like I don't know anything about customs or international shipping, and actually that I hired somebody on Craigslist to help me with shipping and stuff, and she checked the wrong box on the DHL website and made it like sender pays the customs fees, and so it was like a $5,000 order, but I had like $4,000 of import duties and that I got a bill for like 6 months later after she was long gone. But yeah. So anyway, yeah, there was a worldwide, people all over the world were customers from early on. A lot, of course, heavy U.S., but yeah, all over. So, but the first thing we built with it, right? Yes, I'm just rambling. I mean, we did a lot of FM radio was an early one. Then we, obviously the HDTV was the first sort of real accomplishment of a system. We did. You remember iFob 2? No, there was that meme that all your base are belong to us. So I wrote all your frequency are belong to us, and it transmitted the same thing on like every ham repeater channel, and so no matter what you tuned so I would do this like demo for hams, and I would say, okay, take out your HT and turn to all of the different frequencies, and it was just me saying the same thing over and over again, no matter what channel they tuned to, and that was like sort of like here's the power of software radio. It's not just you can do one thing, you can do like 50 things at once. That was a fun one.
And so, Eric, I mean, you had the HDTV, which was, I mean, a contracted piece there and a contracted motivation for the project, but personal projects or utilities that came along the way?
You know, there's a part about when you're starting from the beginning, there's not a whole lot of like, oh gee, what am I gonna do on my weekend when you're like building this thing out? So, I mean, originally, we just started with like the broadcast FM receiver because it's very accessible and easy and could show the thing like you could receive more than one channel and tune more than one thing at a time because we're like a broadband-ish, you know, receiver with that cable modem. We could get like half of the broadcast FM bandwidth, I think. No, I wasn't like I was looking for more trouble. It was just kind of like, let's get this thing. The other thing to realize at the time in this kind of 2001 framework, and the ATS thing probably took a total of like 2 years by the time it was a kind of we started with this MIT code to just kind of, because there was some code that existed called P-Spectra, and like, let's go give it a try, and we built like GNU Radio 0.9, and then it was kind of like, that really wasn't a great solid foundation for the future, and John Gilmore, who was funding me at the time, I'm very happy that he said yes when I said that thing you're never supposed to do, which is I'd like to start over, please. You know, so we had that opportunity, which really became the foundation of what we have today. Of course, it's been evolved over 20 years.
So with that as, you know, the initiating project with the HGTV and ATSC, with, you know, your initial kind of specifications for the radio and your goals for low cost and the capabilities and USB2, defining some of the bandwidth, you know, kind of what were some of the early decisions that were made which you feel have shaped the way that GNU Radio has evolved, for good, for bad? You know, you in many ways helped define what it is to be GNU Radio, and as we move into GNU Radio 4, we're still using many of the same terminologies and pieces, at least as far as I've seen.
Well, at the beginning, it was only had the streaming model with it, which turned out it worked for our first few use cases. It was fine. Broadcast FM, you got the streaming data coming in, no problem. And the streaming model came up kind of like it was how I would, in one sense, it would be like how you would build hardware. There was just this bus, things clocked along, and there was different processing that happened, and it sort of made sense. Where that kind of began to see little rough spots is once you start building kind of like packet-based modems and things like this, there seems to be generally a discontinuity between what we call the PHY or the physical layer, where I'm out there kind of correlating, and where's my header, and then all of a sudden now I'm dealing with blocks of data. So there was this rough spot in there about how do I get from stream of samples into things that look like, you know, packets, PDUs. And that started pushing at a certain point it just became, you can't do everything in the streaming model. Or you can try to kludge a bunch of things around it, but it gets super awkward. But that said, there's still a streaming model in there, and for certain classes of problems, it's the natural occurrence. And then we did other things, like, oh, we'll add tags to it. We'll put metadata in the stream.
Okay. And, I mean, in defining the hardware, do you think there was anything that set a tone right from your initial spec that's carried forward that, you know, was either good or bad? Did you draw a box that the community has, you know, and community and industry has kind of followed? You know, not that this was the first SDR, but
yeah,
in our context, it's quite a prominent one.
Yeah, well, I mean, the block diagram really today is the same, right? You've got RF front end, A to Ds, D to As, FPGA, and some interface to processing, and sometimes that processing is local and it's not over a USB or an Ethernet or whatever, but the same model is sort of in every SDR now to some degree. Although, I mean, not all of them have an FPGA, but they all have some sort of, you know, digital adaptation between, you know, samples from an A to D and into the host. I think one of the best decisions I made was to, you know, have interchangeable RF cards, and that was that was very important. I mean, if you remember, the first few daughter boards we had were very narrow band. That's just because the chips that were available were at low cost were narrow band. Like there was the RFX 400 board. It would cover 400 to 500 megahertz, and there was the RFX 900, which did 800 to 1,000, right? And so so you had to interchange them to cover any sort of interesting larger range. But a few years after that, basically the chip vendors like Analog Devices and TI started making chips that were much wider band, and we were able to cover more significant blocks of spectrum. So then it went to there was like the SBX board, for example. That was I don't know, that one was like what was the SBX? SBX was like, I don't know, 1,000 to 3,000 or something like that.
Yeah, like 1.2 gig and above, I think.
Yeah, it was like 1.2 to 4.4 or something like that, and then there was and then eventually there was the UBX that went 50 meg to 6 gig, and at that point you didn't really need to plug them on and off anymore, and so it wasn't necessarily that useful at that point to have interchangeable RF front ends if you just buy one, plug it on, and it's always on there. But from a building it and designing it and verifying it perspective, that still makes sense.
So given that there was that pluggable design, on GNU Radio we have these pluggable blocks people bring in out of tree modules. Did you see anybody design custom front ends, and was that something that was in your mind as you were looking at this?
Yeah.
And what are some of the interesting applications you've seen?
Yeah. So so one of the intentions was that it was an open interface and you could design your own front end for it. So there weren't a lot of people who did sort of custom stuff, and there were a few like people who contracted with my company to make a custom front end for their purposes, like the LFRX, LFTX that came out of a custom development for a University of Washington, actually, so not far from here. But Epic, their first product was a usurped daughter board. That it was a wideband receiver. This is before I had the SBX, and they had made a receiver that I think covered about 1 gig to 4.4 gig or something. So that's kind of how they got their start. So in that sense, it was successful. It's obviously a very successful company, and quite a big business today. So at some point, early on, I thought there would be dozens of different boards that were interchangeable. As things got wider, you needed fewer of them. But yeah, I think it worked out in that sense.
And are there products that haven't been built that you kind of expected to be, whether by yourself or by other companies and groups, kind of using this kind of model?
Well, I'm surprised there's not more work above 6 gigahertz. I had sort of always intended to keep making daughter boards to higher and higher frequencies, but it turns out that first the vast majority of the sort of interesting stuff happens 6 gigahertz and below, or maybe 7 gigahertz now. Higher frequencies have other issues where you very often you want to integrate the antenna. You don't kind of want the signal going across a coax. And so, like for millimeter wave, right? Like you can do things with an SDR at millimeter wave, but it doesn't always make sense to just have like a board that plugs on. It's a more specialized device. So you haven't seen as much of the higher frequency stuff as I expected. And I sort of expected much wider MIMO to happen. I think we see like up to 4x pretty commonly, but
more channels, more specialization of hardware for specific applications.
Yeah.
So looking at, that's an evolution of a product line. With GNU Radio evolving over time, are there trajectories that you've noticed over the entire course of the lifespan of the project and where we are now and looking forwards that you think have been specific trends of development or interesting things that have been started but not finished along the way. GNU Radio has had a long development history. Are there pieces that are yet left uncompleted that were attempted earlier, or things that are started now that you think are particularly good or bad? Nice. Eric.
Well, I think there's a lot of things. I mean, the basic architecture is real. I mean, it's been evolving, but it's pretty much the same as it was from the beginning. And I'm really happy about GR4 as, in one sense, quote, clean start, to solve some specific problems that the folks in Germany at the particle accelerator had. But they wanted really high performance, and they had some concerns about like safety critical kind of a thing, and using very modern C++ that gets you a whole bunch of stuff you can do that we didn't do in the past, but partly the language wasn't there. And it was driven, in one sense, from their point of view, it was driven by, truthfully, I was always, what's the simplest thing that could possibly work, knowing you could always fix it later, right? And so, but there were some things all along the way that were inconvenient and hard to do, things like burst mode modems, which once you get past, hey, I wanna, listen to the FM band or something like this, you get to be, or even you take a thing like you want to build the equivalent of a handy-talkie kind of thing where you've got two-directional traffic. There's this whole thing about things that didn't work well in GR3, and people worked around it, but it's about managing latency, for example. Yay, real time, come on, raise your hand. Yes, okay. And this is great, just a shout out for how the community is working, is that there are people here who are deeply interested in provable, what we could call hard real-time scheduling and bounded latency and throughput and being able to do all that. So, yay. But in the existing GNU Radio framework, that is rugged. And this whole idea of how do you get, there were 3 papers, I think, presented so far that had to do with ground penetrating radar. Now, it's not the first time radar has been around, but it's the ground penetrating radar session. And all those people have this question about, well, how do I transmit and receive? And you need precise timing. And it's worked in there, but it's not super obvious how to do it because people always ask questions about it. So I just really think that in this one sense, new start, fresh people, that have got appetite for a better way to do it and willing to invest, in their case, years of development, engineering years has gone into building the 4.0 framework.
So you touched on some aspects of the latency and the constraints on the systems and security, but one of the big pushes that has come out of GR4 and running on a particle accelerator, and also FAIR being a German national government-funded organization, is that they're bound by the increasing number of software coding standards and software reliability standards. C++ memory handling is inherently unsafe, but, and now using modern standards to address that. Both of you, have not only done GNU Radio and USERPs, but have worked on developing commercial, critical systems that have to be performant, have to run. Are there pieces that GNU Radio and SDR systems need to be addressing to meet that? And do you feel like GNU Radio is trending in that direction, or are there pieces that need to be looked at for, both enforced outside standards and internal system requirements if you're actually building a system?
Well, so I don't know if this is exactly an answer to that, but I think Eric touched on the sort of the streaming model, and then that gets you a really long way in a lot of SDR problems, but it doesn't do everything. And so you always had this impedance mismatch with, okay, now I want packetized data, and I want, to do protocols and upper layer stuff, and some of it fits in the model, some of it doesn't, and then there's always issues about how do we use alternative compute, so do we do, how do we work GPUs in, and how do we work other accelerators and things, and stepping back after when I was more active in, in the earlier days, I sort of had this vision that GNU Radio would do everything. Like you could write anything that uses wireless communication or radio waves at all could be done in GNU Radio. And I saw anything that wasn't, like if there was no 3G implementation written in GNU Radio, that was like a failure. And I realize now that is actually that's not a failure. There's just different tools for different jobs. And yes, SDR, like when you tell somebody about SDR for the first time, you say, oh, like I can, you can write software and you can make the same hardware do, garage door openers and Wi-Fi and all this stuff. And like in theory, yes. In practice, there's still a lot more specialization, and everything's not just sort of completely interchangeable like we had this vision of. So, like the Wi-Fi chip in your phone is very much a software radio, and the cellular chip in your phone is also very much a software radio. But they never do each other's things, and there's a completely separate chip, and it's architected totally differently. And the reality is like there's this sort of engineering beauty that you would see in like, oh, I could have one piece of hardware that really does everything. In practice, it just doesn't happen. And I saw that for GNU radios. Oh, like GNU radio should be doing 3G, but the reality is GNU radio is incredibly good at certain things, and rapid prototyping, learning, experimentation, and all that stuff. And it doesn't mean we need like Wi-Fi, people doing their real Wi-Fi systems using GNU radio, right? It's not really needed.
So not Wi-Fi or a 3GPP standard, but I mean, both of you have deployed commercial applications where GNU radio is the answer for the DSP of that. And what drove that choice? What did make it good for that? And why didn't you use something else? And are there pieces that were clunky along the way, or what did make it a good candidate for that? Nice. Eric, if you.
There's some cases where you've got, let's say, a relatively low volume system you want to build, and it has some specific requirements that aren't met by some existing commercial system. Some of the vendors around here have space-related stuff. And in spacecraft, the worldwide market for radios is kind of like relatively small. Now you have Starlinks, and it's a whole other order of magnitude more of them, but there's certain things where it's the flexibility of the framework is sufficient to solve the problem. And for example, if you wanted to, you think about spacecraft, let's take a spacecraft example, because there's things like, there's Doppler involved. And like, most radios you buy don't have a thing where I can feed in the orbital parameters and have the radio automatically track out the Doppler. Where I want a radio where I can put this in and it'll steer, on the fly. So there's certain problems where it's just nice, I can have my little tweak that I need that makes the problem I'm trying to solve so much easier.
Yeah, and again, there's no one tool. Like, if you look at Swiss Army knives that have like 50 different tools, they're all terrible, right? It's not good at, so making one thing that really does everything is not always the right answer. But GNU Radio does an incredibly large set of things very well, and I have deployed a very real set, like the satellite texting service that is on iPhones now. That's my former employer. That is running GNU Radio in a data center, in these ground stations with giant piles of servers and GPUs. It is doing all the mod and demod in GNU Radio. A lot of custom blocks, of course, and sort of custom way of sort of farming out, massive amounts of search to 40-something GPUs to find signals, very weak signals and noise. But that's all running GNU Radio. And actually, the early demos of the user equipment side in the phone were also running GNU Radio. That was just for demos that didn't ship, but we ported GNU Radio to the main processor in the iPhone, right? And actually, even before that, we had it on laptops with a cable into the antennas of the iPhone. First ThinkPads, and then the VP of the MacBook division was like, You got to switch. So we switched over to Macs at that point, and then eventually ported that into the application processor of the phone, and then eventually it got just ported into the cellular chip of the phone. So it has like a DSP unit, and Qualcomm gave us a little cutout of where we could put some code. And so we wrote our software radio in there. And so, yeah, at that point there was no GNU radio anymore, but the back end is all GNU radio. Now, we didn't do the Mac necessarily in GNU radio, we did the Phi, and then the Mac is actually in Python. And it talks to GNU radio on one end, and it talks to the cloud and Redis and all sorts of, cloud networking technologies on the other end, and that's in operation in roughly 30 ground stations around the world.
The question that I had been riffing off of, but I think that the speaker had, the question had a slightly different bent on it than I asked, was how should GNU Radio engage with safety, cybersecurity, and product liability without losing hacker velocity? So, the code safety was one note there, but, in a world of thinner grassroots open source software and growing vendor lock-in, how does GNU Radio stay relevant? Was their question, which I think is substantially different than how I phrased it. So, do either of you have
I also
thoughts
may
on that?
not have answered exactly how you phrased it anyway.
Can you just give me the question again?
Yeah. So, with product liability, cybersecurity, and safety being something that is being pushed more towards software implementers, we see this with the SBOM and other security initiatives from large companies and organizations and standards. GNU Radio ends up supplying a software toolkit, not necessarily a product. And we rely a lot on volunteers and hacker velocity to, be what GNU Radio is or has been. Where do we go in the future? What needs to be done, and how do we stay relevant as a project, given that context?
All right. So this is Eric Blossom speaking, not associated with anybody. This is my unfiltered opinion that the GNU Radio project is never going to go get any kind of safety certification done for any of y'all, right? And there's a part about what do people want and what are they willing to do, like from a best practices point of view, that we could evolve the thing into. But it doesn't mean we don't like that idea, but it's just a free software thing that the people who want to do that are not paying us to do that. So there's a kind of a piece in, I like the question, but it kind of also points to the kind of sometimes talking about there's the givers and the takers in a free software economy. And they may want something that we're just not going to provide. Doesn't mean that we don't think it's a great thing, but some of this thing is very expensive. You talk about certification of any kind. I mean, like, a thing that I have never built in my software career are, for example, things like the software that runs your ABS system. And I've talked to people who worked for, major German manufacturers who told me how that went. And I was like, wow, so happy I wasn't doing that. It's critical, and somebody wants to do it. And, but I think to look to a community-driven project is not the place to get that.
Yeah, I think obviously any development should be done to the best standards possible, and security needs to be something that's thought at all levels. But in terms of certification, certainly any application is somebody's building on top of GNU Radio, and if they need certification, that's really going to be on them. But it's great to give a good base for that. So you should be, you should always be, any piece of code you should be thinking about security for it. There's people who do that sort of thing for for Linux and embedded Linux and things like that. And it's huge organizations and industry consortia, and it's a consortium of people who care about it. And so anyone who cares about that, I think it's going to be up to their organization to do that sort of thing.
So 2026, the founding of the GNU Radio Industrial Consortium, chasing down these standards, soliciting funding for a security audit, you know, these sorts of reviews.
Yeah.
Is
that
that
needs a board of directors and yeah, all sorts of fun stuff like that. Yeah.
nominations? Anybody?
Yeah, I think an example, not related to GNU Radio, but is what is it, Zephyr, right? It's the
Embedded RTOS.
Yeah, an embedded RTOS under the Linux Foundation. But part of what they wanted, a bunch of like very gigantic companies wanted to only have to certify once. And they got together and said, how about we pick this one thing that's pretty close to what we want, and then we'll put all of our attention on that, and they'll end up with they'll take all of their resources and only have to solve the problem once.
Something I tried pitching informally and briefly was the idea of a DSP correctness audit of the block library.
That'd be nice.
Has anyone ever found a DSP bug in GNU Radio? No, right? All of our implementations are perfect. But we do use those as the building blocks of so many applications. Wouldn't it be great to get some organization to fund a couple of PhD students or master's students to work for a year or two to start chipping through the blocks and audit what we have there. So yeah, looking forward, we have this industry consortium that we're now going to spin up next year. But we are addressing the question of licensing. GNU Radio 4, the core runtime, moving to MIT is very much on the table. I think at this point it's an expectation that that's going to happen. But how do you feel about that? And we had this talk this morning, which definitely was bent in the other direction. But what does GNU Radio as a community do with this? And
Yeah.
Uh,
Uh,
the extended ecosystem. How does this make?
This is fascinating. So I talked to Bradley, who's departed. Oh, no, he's still here. So there's I suggested another alternative that could work for all parties involved. It still requires, licensing and the conversation around different repos and all that. So I would say that it's a work in progress right now, and we want to get all the stakeholders in the game on in this alternate conversation, because it's sort of like in one sense there was some consensus building. So this doesn't push this thing out far, but it's like, hey, another possible solution that could work for everybody.
So I was always a very, very strong GPL believer. I wanted to make sure that everyone gave back and all that. And I think the outside of GNU Radio, the rest of the world of software or open source software seems to be sort of moving away from that, and there's much more that's sort of any of the, million different permissive licenses. And that seems to be where things are going, but it's also because that seems to be where industry wants to go, and industry is funding much of that development. But then you also see like a lot of those companies then, like Redis, I think, for example, is like, holy shit, everybody else is making money off of this and we're not making money off of it. So what do? Okay, let's create this non-open source license and piss everybody off, and then just everybody's mad at them, yet they gave away this thing, and it just there's not a good answer, right? But when it comes to GNU Radio, I'm gonna maybe this is controversial, and I don't know if I 100% believe this, but I think the whole thing may actually matter less than we really think. If the goal is to get people using GNU Radio who aren't currently because of the license, do we know that there are people who could otherwise be using GNU Radio and aren't because of the license? And because I think a lot of what GNU Radio is used for is not necessarily for technical reasons and because of what it is not necessarily something that becomes an end user app where anyone would be concerned about the nature of the GPL. So are there instances where you you end up not using it because of that. Maybe, maybe not. It may not even, so like, okay, so the application that we did at Apple, that uses GNU Radio, it wasn't impacted by the GPL because it's an infrastructure that we own.
You're your own customer.
Yeah.
That there's no distribution of your
Yes,
code
and I no
base.
longer work at Apple, by the way, as of January, but, so it didn't matter there. It didn't impact us. It did cause the lawyers, of course, freaked out and had to have a lot of meetings because I was like, no, it won't impact us. And they're like, eventually they, wasted a lot of lawyer time and a lot of my time, but they've realized, okay, it doesn't matter. But are there applications where is there any reason to be putting GNU Radio in a phone or something? Like, there may not be, right? GNU Radio is used in a different way than that. Now, which license it has may not matter. But yeah, from a philosophical point, I believe in the, okay, give back what you can that improves the situation for the community, and you may be able to get that with a more permissive license if you have that community ethos. But yeah, I don't know. That was a very long non-answer maybe, but.
I liked Eric's answer. Just a time check. Are we at the end of time right now, or are we? 10 minutes. Great. Okay. I didn't know if we had an hour. Wonderful. We are near the end of the deck of cards, which means that we get to go to some of the more fun ones. What's the most fun or outrageous thing you've done as a result of GNU Radio, but generally the community or SDR, this whole experience of being part of the project and meeting people?
Yeah, the meeting people has been really one of my favorite parts of the whole thing. I mean, part of it is like a strange bedfellows kind of a thing. We're like, wow, people I never thought I'd be interacting with are like now friends of mine. I have to say again that like last year at the GNU Radio EU Days that was held at the GSI Fair facility, this gargantuan particle accelerator. It's like doing research on heavy ions and antiprotons is the future piece of it. Was super fun. I mean, it was really fun. Like, who would have ever thought? I mean, like, that they're using GNU Radio in a way that I never dreamed of. I mean, they're not even really doing a whole lot of signal processing with it. It's more like, oh my God, they're using all the rest of it, which was like shocking in a good way. Plus, it's just a whole other community. And then in that particular culture, it was really interesting to that because about half of the attendees were some kind of physicist or not, and then there were some software people, but it was a whole other community of people. That's I guess the most recent example, but just like people from all walks of life doing, things with GNU Radio or had a question about it or an interest in it. And part of the kind of things that, particularly because it's a free software foundation, is some of the things that Bradley was talking about today on how it was used in the service of policy to support really freedom for all of us. Big fan of that.
Yeah, I mean, from my perspective, I got into the whole thing to be a user of this, and I ended up sort of just making tools that then other people used, and I sort of lived vicariously through the cool applications that people made. And so, some of the wild ones were there was someone who tracked the muskrats in Ithaca, New York, using GNU Radio in the very, very early days. There were people doing scientific research with magnetic resonance force microscopy, and then there's the people who, I always love seeing the interesting security research and the hacks of, proving security vulnerabilities in GSM, or even now you see it with 5G, and there's always a USERP or GNU Radio or something involved, and that's always really fun. Remember that paper where they did the pacemakers, they had a USERP connected to a pacemaker, and then the pacemaker doesn't function unless it senses a heart that it's connected to. So they simulated a heart with like ground beef and bacon, and this was in the paper, and it was, you know, like those things were just always fun. Like I never envisioned using it. I just wanted to experiment with OFDM and MIMO and stuff, right? And people have done all sorts of wild things with it.
And to just really follow on with that, there have been a huge number of systems that have some kind of wireless piece in them that have been, security was not even a thought. It was like, oh, nobody will ever go there, like implantable medical devices, you know, and it's kind of like terrifying when you think about it. And, you know, a while back there was all the sort of smart cards and how secure are they? Or, you know, attacks against SIMs and side channel attacks against all this stuff. And I think that's a thing that I've found. I'm happy that GNU Radio and the tools are available to people and that they've been able to use it to basically go after some of these things, to poke around, as opposed to trust us. It's like fine. It's only your, you know, it's only your whole wallet of stuff. Is, you know, I like that part. Yeah.
So we got some of the outrageous there. Is there anything else that pops to mind that is shareable that really nails into that outrageous piece?
I don't know. I mean, I've seen people use it for art installations, like sensing where someone is and then changing the lighting. And there's this group at MIT that has done this sensing, you know, listening to heartbeats and finding people behind walls and you know, doing the sort of like the I fall and I can't get up kind of thing with you know, with radio. And I'm sure there's others that I'm blanking on now, but there's just been so many, you know, different things people have done.
And there have been things in that same kind of realm of things you're not supposed to know about or do. You know, there's like, oh, you have a really general purpose like receiver, and you know, you can kind of put as much front end on it as you need, and you could go do these like quote tempest attacks on things, or you know, you could sniff things that you know you weren't supposed to. And it wasn't even a question of whether it was legal or not. It was just kind of like, oh, look at that. That thing radiates on my keyboard when I type on it. You know, whoa. I always wondered, for example, about like, I've been known to use like, you know, the little dongle that fits in the mouse. And, you know, I kind of always was highly suspicious of how secure that was. You know, I wasn't personally going to go invest too much time on it, but, you know, sure enough, there's a paper saying, you know, and then there's like, oh, it turns out those little dongles have firmware that can be updated in them, and something was changed, you know? Like, okay. Oh, restaurant pagers. Oh, yeah.
Yes.
Your meal is ready.
I was
Local
trolled by that one,
bar,
yes. Yeah.
yeah, the local barbecue place in Mountain View, or Sunnyvale or Mountain View. Yeah, closed now, unfortunately.
Wait, which place?
The one that was right next to Stanford Shopping Center. Oasis.
Oh, okay. I don't know that one.
Yeah. So the last question is, as we wrap up, both of you have been involved in interviewing and hiring people, not just recently, but for some time. But what skills or knowledge do you look for, or do you feel are often missed in the people that you're interviewing, not just as beginners, as intermediate or advanced people at different stages in their career? What do you look for, and what do you not necessarily recommend people go and learn, but think are missed topics or are skills which are overlooked sometimes?
I got a couple of ones. A couple of things is, you know, a person comes up to you, sorry, this is like the on the record, off the record conversation, but if they don't look like they're alive, that there is no light in their eyes, I'm not hiring them. The other thing is that, and related to that, I think, is a fundamental, like, are they curious about the world? I mean, you know, are they curious? Because if they're generally curious about the world, there's a pretty good chance they're curious about maybe the kind of thing that I'm interested in them working on. And again, really, being us, we are human beings. We are social creatures. And I know that there are, you know, if you want to work with other people, it's really great to have skills of communication, like empathy, rapport. These are all like super important. I mean, there's been things done by like a person in a corner that never came out for 5 years and then came out with a great thing, but that's not, we don't go looking to hire those folks for the most part. So those are the things I could think of that really, for me, I really look for. Like, is this like a sense of humor and like, enthusiasm?
Yeah. I mean, I look for someone who's passionate about what they do, and doing something as a hobby is evidence of that, right? If someone has, a hobby project, even if it's, something simple, but they're working in this technology because they think it's fun and they're doing it in their spare time, or they're starting things on their own, or they're contributing to an open source project, that's a big plus versus the giant pile of resumes you see when you're hiring, where yes, they can list 20 technologies that they've used in this day job that check all the boxes, but are they excited about it? And the best engineers I've found have always been people who would be doing it even if you didn't pay them. And that's how I found a lot of the people that I hired in their, especially in the early days at Edis Research, was they're already in the on the mailing list. They're all answering questions, or they're contributing, and nobody's paying them. It's like, oh, I should find a way to pay this person, and that worked very well for me.
I think another thing is, what have you built?
Yeah.
And I don't even really care the domain. Tell me something you built. Because partly that's a demonstration of like ability to create in the universe. That they cared about something, they went out and figured out how to do it. They built something, And if it was software, awesome. But also, I mean, a long way, you built some other thing. It's all good.
Do you have any last closing thoughts or a question for each other of anything which fits into kind of the overarching themes that we've touched on?
I don't know. Closing thoughts. I don't know. I mean, look, it's 20 years of the USERP, 20 years of the USERP now, and 25-ish of GNU Radio, and it's obviously changed my life quite a bit. Good portion of the people at my wedding, who were people I met through this, and people who I'm friends with, and or worked with, or just knew through the community, and it's more than just like a day job, right? It's the whole thing's been life changing, and it's really. I don't know, if I hadn't seen that thing on Fresh Meat or whatever, and or if I hadn't, or if John Gilmore hadn't, found that, hooked us up with Jay LaPro and at University of Utah, I'd be at some random Bluetooth chip company, and things would have been very different. So I'm just incredibly thankful for the whole ride. It's been awesome. So.
Something that really, I guess, that I would kind of lead with is, or wrap up with, was that the idea of partnership and community and building things together, and the care of the community. Like, one of my favorite things about the GNU Radio community is that I stepped away a long time ago. I mean, I was there the first 9 years as a full-time thing. And I think it's one of my most, things I'm most happy about is that the project has continued on in good hands, that the community is a friendly, welcoming place. I mean, it's great. It's like, not an accident that this happened. And that I really, I'm so happy that it's continued on, and that there'll be the next set of people that are on it, as long as we keep it, that it's relevant. And I think part of it is just like this GR4 is like the next part of, like, for example, we could build higher speed radios where there's a certain point, like on some of the high speed radios I built, Before, they were just way higher speed. We're not doing them on a CPU. We're going to do them on an FPGA and they're coded in Verilog or whatever, right? But one could envision a future where, wow, we have higher level, there's all kinds of higher level language. But it's like higher level language that could target all kinds of things, as a future. But again, back to community and people and partnership, and those are the things that are important to me. And as my wife, we've had an ongoing conversation, and one of the things is that everything, the assertion is that everything happens in relationship. So.
Well, thank you both for your relationship with the project, and in so many ways, all of us able to have a relationship with what you've created. So thank you very much. And I've been told that lunch is not quite ready, so don't rush. But you both are around the rest of today and at least, yeah, first half of tomorrow. So I think I got through the stack of questions pretty much. But if you have more questions and follow up and lead on ones, please do find them while they are not quite eating lunch, but let them have a bite first. And the conversation will certainly continue. So, thank you.
Thank you.
Thank you.
All right, so I'm Mark, and I currently lead the SIG-MF project with Jacob Gilbert. So out of curiosity, who here has used SIG-MF either at work or for personal use or whatever? All right, not bad. Yeah, so this talk is going to be all about storing RF to files, so recording RF or saving recordings. It's not going to be about the actual hardware used to do it. SIG-MF is an open standard for how to store RF to a file. You may already know about binary IQ files. Well, SIG-MF is essentially taking a binary IQ file and adding a metadata file to go with it. And SIG-MF defines that meta file, which we use JSON. So it has a JSON schema for defining that metadata. And like any open standard, it forces shared and kind of, we think of it as proper documentation of the critical metadata that goes along with an RF recording. So the alternative to SIG-MF could be putting your center frequency and your sample rate in the file name, which I see plenty of people do. That's certainly one way to do it. But over time, that could lead to bit rot and such. So now, SIG-MF, it gives you a lot of potential ways to, there's a lot of optional fields. So if you want to specify something related to your recording, there's probably a way to do it in SIG-MF. But for this talk, I'm going to try to focus on just the basics, because that's typically where folks start. The other thing it can do is give a way to annotate a recording that was already created. If you want to put a bounding box over a certain time frequency range or just a time range, we call that an annotation, and we have a way to do that. Now, just a quick example of the metadata, just so new folks can get a feel for what it looks like. It's in JSON, so not that readable, but the metadata is split up into three categories: the global, captures, and annotation segments. And in the global, you have your typical data type, sample rate, a bunch of optional fields about the hardware and the description. The only required one is the data type, sample rate, and the SIG-MF version. And then in captures, that's meant for if you're changing the frequency or you're stopping and starting in the same file. But if you don't do that, you just have one capture that starts at sample 0, and that's where the center frequency is stored. So it's actually not in the global. There's no global center frequency. The date time there is optional. And then annotations is a list of these objects. And I've got one annotation shown here. You can see how it's kind of a time frequency bounding box with an optional label. There's some other fields for description and such if you want. Now, as far as that data type you saw here, this defines the actual IQ file. And here's a quick little reference. So the only real thing to remember is that the I corresponds to a signed integer. But you'll typically be using the 32-bit floats, where both I and Q are each 32-bit floats, same as NumPy's complex 64. That's the typical GNU radio blue sample stream, and tends to be the most common way folks are saving it. But if you want to save a bit of data, you can save your samples as shorts, which is what the Blade RF will do by default. And then for stuff like the RTL and the Hack RF, you'll sometimes see the 8-bit options. But these are, this list here is pretty much the main options as far as what you'll see in the real world. And then why use something like SIG-MF? Well, there is a lot of software out there that can read or write SIG-MF recordings, so you're immediately able to use that software with your recordings. You can use a file source block in GNU Radio and load in any old IQ file, but it's just going to be the data. So for example, like in Spectrum, you can open a SIG-MF recording, and it's going to copy the sample rate and some other information directly from the meta file. So that saves you one step. The other reason to use really any clean method of storing metadata is to avoid bit rot of data sets. I've certainly worked places where the metadata was maybe in an email or a CSV file, and somewhere along the way, like a year or two later, that metadata is gone, and we're trying to figure out what was the sample rate and the data type. So avoiding that kind of situation. There's a lot of potential for collaborative processing and analysis if that's the kind of thing you're into, especially on the annotation side. You can take a SIG-MF recording, that already has all the metadata listed out, and then add on annotations. So if you want to represent your like machine learning classifier results or detector results, that's a great use of annotations. But really, the main reason is because it's the alternative to some bespoke method. Now there is, as far as what else is out there in terms of standards, there's a bunch of proprietary formats, like the test equipment vendors typically have some format when you go to save IQ. Recently I learned about this ITU standard, but I read through it and it's extremely specific to spectrum sensors, like industrial spectrum sensing systems. So it's HDF5 based, but I think most folks probably wouldn't be too enthused about it unless they were creating a spectrum sensor. And then the other thing I'll see is packet captures like Vita49 saved to a file, but you end up storing a lot more information than you have to in those cases. There's also some old legacy formats that I know some of you use, and sometimes there's no other option, but they tend to be kind of overly flexible, leading to different variants and not an actual shared standard. A quick history of SIGMF. It started in 2017 at a DARPA Hackfest by Ben Hilburn and some other folks, and it became a GNU Radio sub-project, kind of like Volk. I think those are the two main sub-projects within the GNU Radio organization. And there's actually a GRCon paper that kind of describes a lot of the motivations behind the decisions that Ben and the others had made. But over that point, it was slowly refined. We added some extensions, and it went into a stable state probably around 1 or 2 years after this. So not a lot has changed, and that's for the best, I think. Last year, that's kind of silly note, we kind of changed it from being a shorthand version of the signal metadata format to just straight SIGMF, and that was mainly for Wikipedia, because they want to have the full name of something as the title. But yeah. Now, as far as where to find the specs, if you want to look at all the other optional fields I mentioned, sigmf.org gives you essentially a visualization of the JSON schema, so you can look through all the different fields, and there's a little introduction at the top about it. You can also get a PDF of that exact same content. The actual schema and the description of each field all lives in a single JSON schema file, and then the extra markdown file is just for the introductory part. But that main JSON file is in the root of our repo. So it's in the SIGMF GitHub organization. Now, as far as GNU Radio, unfortunately, we've been kind of stuck with these SIGMF minimal blocks that were thrown together a few years ago, and that was mostly due to some failed attempts at making a robust GR SIGMF that would do everything we needed to do. So it's better than nothing, but these blocks are pretty much just a light wrapper around the file source and sync blocks. They're not going to automatically change your data type, for example. You have to know that coming into it. But they will, the sync block is pretty useful because you can enter in all the metadata you want to add, and it'll make the file for you, the JSON file. But there's also Jacob's GR SIGMF utils. It's really not a full out-of-tree module for SIGMF. It's more of little utilities that were missed, and I list them out here. So we definitely appreciate Jacob's effort there. But yeah, so we're looking for a group or an individual who would be willing to kind of lead a GR SIGMF, and there would be a lot of work to go off of that has been done. I know SkySafe did some work early on. So it would be up to you to kind of architect it and decide what you want to keep or reinvent from previous attempts. Now, outside of GNU Radio, if you're using Python, first I'll say that if you want to use SIGMF in a very basic way, you don't need any library. Most languages have a very easy way to create a JSON file based on a dictionary. So you can create your dictionary with the minimal information you need, make the JSON file, you're done. You don't even need this library. But if you want to use the more advanced features of SIGMF, we do have a library for that. And this is the only real SIGMF library maintained by the GNU Radio and the SIGMF folks. There might be a C++ one coming, depending on how some approval for releases go. And yeah, this library can support collections and archives and all of that. And a huge thanks to Kyle, who maintains that library. and a bunch of other contributors who help. Also, Glenn has been really helpful with refining the spec and being involved in discussions, so huge thanks to them. There haven't been a ton of updates since last year. We had a release that added the ability to add geolocation to captures, which was asked for again and again, because if you have a moving node, a receiver, whatever, and there was no other way to represent moving coordinates. So now you can make a new capture segment for each time you get a coordinate update. We still have the captures, the coordinate geolocation field is still in the global, but we now prefer that folks use the captures segment instead. And then what was announced last year is we're recommending folks, if you have multiple elements and you're doing multi-antenna receiving to a file, that you use the collections method, not the num channels. Num channels will interleave the samples into one file, and you end up losing most software interoperability at that point. We actually have a Wikipedia page now. It was finally approved, and this is a screenshot showing an adoption section. So if anyone has been using SIGMF somewhere where you're allowed to share, feel free to edit that page and add your name there. But here are some examples of people using SIGMF. And here's a little more information about who's using it. NTIA has always been very big on SIGMF from close to the start. They have a lot of their own extensions that they use internally, but they also keep a public GitHub repo. Yeah, GNU Radio really only has basic support, unfortunately, but hopefully one day that changes. MATLAB does have a SIGMF function, but it's not going to be what you think it is. I think it's like sigmoid. It's not our SIGMF. Lastly, I wanted to point out IQ Engine is a tool that I built a couple years ago. It's a purely web-based tool for managing a lot of SIGMF recordings. And we have a public instance of it hosted at iqengine.org, which you can use to get example recordings. So you can download the data and meta file. It has all the previous CTF recordings. And then if you go to iqengine.org, you can, on the left, open your own SIGMF recording or a directory of a bunch of them. And it's all client-side viewing. It's kind of like an InSpectrum-style viewer. There's also a mini tutorial for SIGMF for beginners. If you go to iqengine.org at the top right, hit the SIGMF link. It includes a JSON validator, so you can just paste it in and it'll check if it's valid JSON and if it's valid SIGMF. As far as next steps goes, we want to keep increasing adoption. We've already had great adoption. There's been a lot of talk about converters because there's a lot that exists as far as going from other formats to SIGMF. But as far as getting a standard place for them to live and making it easy for people to use them is currently what we're trying to figure out. So if you have any recommendations, reach out to me, go to the SIGMF main repo. You could make a new issue just proposing ideas. And I already mentioned the GR SIGMF. So with that, I'll take maybe one question we have time for. No questions on SIGMF? Everyone knows about it already by now? All right, well, yeah, thank you. Yeah, that mic. Actually, if you hit the switch on that mic, it'll work.
We've gotten burned by that before. Me? Yeah, okay. I guess we're ready to go. Hi, my name's Troy Bates. I'm going to present on FPGA acceleration in GNU radio. Kind of a hot topic. I know there's a couple other talks and a few other people that I've been talking throughout the week. I'm kind of approaching this from a kind of new perspective, trying to find a low-cost FPGA and see if we can find a solution for hobbyists, enthusiasts, academia. A little bit about me. I have a bachelor's in computer engineering. Been working in industry for about 8 or 9 years. I'm currently enrolled part-time in my master's at University of Maryland, studying embedded systems. That's actually where this talk originated from. It was a 3-credit semester-long project, so constrain the scope a little bit. I have not solved all the problems, but my day job, 40 hours a week, is I'm a research scientist at Peraton Labs. We have a few people here and a couple talks throughout the week, but I do a ton of FPGA and microprocessor work. So let's get into it. I know we've talked about FPGAs a few times here, so I won't bore you to death with all the words on this very scary slide, but the long story short about an FPGA is it's reprogrammable logic, right? So they typically run at a magnitude slower than a traditional general purpose processor, where an Intel processor might be running at 3 or 4 gigahertz. We run at hundreds of megahertz, but the big advantage is everything is parallel. And one thing that I haven't seen talked about as much is these core components, right? So when we think about FPGAs, we're really stringing together these primitives, right? So we have configurable logic blocks, you know, for basic, want everyone to think of those as kind of like basic arithmetic. So if you want to add things together, if you want to subtract things together, they're really good at doing that. We have DSP slices. That's where you're doing your math, right? So if you're multiplying, you're accumulating, you're doing fancier things, that's where they live. And I bring that up because we'll talk about some of the capabilities of some of these low-cost FPGAs. And when you think about LUTs or lookup tables or DSP slices, I want you to think of those as mathematical operations, right? So what can we do that would be capable with these cheaper devices? And you can see quite a bit, right? So for those who don't want to think about FPGAs, I've been calling this to basically myself Project Kirby, because I think Kirby is a relatively good analogy for what we're trying to do. For those who's familiar with the video game character, Kirby is this pink little squishy guy who likes to run around, and he can jump and he can fly, but his special ability is he sucks up his enemies and steals their powers. And I want to pitch the FPGA acceleration as we're not going to do everything. We've still got the same kind of move set. We can walk, we can run, and think of those as the I/O or the physical logic chips on the board, but when we need to swim, we can suck up the fish, or when we need to do a DSP or an FFT, we can go do that, right? And that's what I'm trying to pitch, right? Simplifying the complexity of the FPGA into 1 or 2 blocks. So this is the board I use. This is the Night Fury 2, some really cool board that someone up in upstate New York developed. It was released a couple years ago, but it was released with hardware from 2012, so that's the best we got to work with here. But the big advantage is it has a no-cost Xilinx license. So if you need to buy a fancy new FPGA, you're looking at thousands of dollars for a license to actually build the images. So this is available. It's supported for at least another 15 years, and it is relatively capable. So we have PCIe Gen 2, that gives us 2 gigabytes of throughput, both up and down. That's enough to do the data rates we talk about here. And the big advantage is it's only $250. So as far as FPGA goes, that's relatively affordable. In the bottom right, you can see some of these primitives that I had highlighted before. We're looking at the bottom number. And when I said, we're a magnitude slower, we're running at 125 megahertz, but we can do 200,000 additions in a single clock cycle, right? And that's really the parallel advantage of an FPGA, or we could do 740 multiplications in a single clock cycle. So there's a strong asterisk there. There's a lot of things that you need to do 100% right in order to do that, but that's what we can do with these relatively cheap boards. This board is becoming harder to get your hands on. I know there's some still available on eBay, but I don't know if the vendor still makes it. So I have pitched some other FPGAs as well too. These kind of step down in speed. The one on the left is actually used to cheat in video games, but it comes unprogrammed, and you could potentially use that. I'm not going to talk long about that here. And then the one on the right gives you an idea of what like a development board, a traditional board from a vendor like Avnet would look like. So we get into more modern FPGAs, PCIe Gen 4. There's a lot more that you can do with these capable boards, but the design works whether you're working on a $100 board or a $20,000 or $30,000 board, as long as you've got PCIe. This is our architecture. So we are actually front-end agnostic. We don't really care what your front end is. I don't even care if you have a front end. If you want to do FPGA acceleration in your front end, you do that, and then we live in parallel, right? So the samples come in from your front end, your ADC, they go into GNU Radio, and then we're just leveraging essentially a AXI, DMA, PCIe, Linux character device. So we push samples in, we pull samples out, and this acceleration block on the right is kind of the magic, right? So in the proof of concept, we're doing something relatively trivial. I have a FIR filter. This is just a Xilinx IP core wrapped up and slapped in here, but in the world of where we could get to, this could be a library of 10, 20, 100 blocks that when you need a matrix inversion, you want someone way smarter than I to do a full Wi-Fi decoder in an FPGA, you slap that block in, you deploy an ML, like an ML core to an FPGA, you could see how this could grow into something much bigger. It's worth pointing out that this board that I started with came with an actual reference project. So they were using the PCIe, they gave us all the software drivers and guides to actually install the board, install the XDMA Xilinx drivers, and they provided what we call like memory copies. So we would take memory from the host computer, we'd write it to the FPGA, and then they'd go write it somewhere else in the host. And they were able to do that quite efficiently. So their code runs a lot faster than mine, but it runs at about 1 gigabyte per second. So we get a sense of what the actual throughput of this board is capable of. Half of our theoretical, but still 1 gigabyte per second is pretty good. All I really did was I plopped a Xilinx IP core into this design. So on the right, we can actually see some of what Vivado offers. This XDMA core in red is an AXI stream. This is just a lightweight data protocol. So you're pushing a parallel data bus with an enable, and that's it. And it goes in red and comes out in blue. And we have effectively accelerated processing, right? There's no clock cycles being used on the host processor beyond writing memory to the character driver, and it's relatively efficient. I wrote 2 blocks. I call them PyKirby. They're on my GitHub, and they're very poorly written, but they exist, and we did okay. You can see on the left, we are using a 1 to 2 half-band FIR filter, so a 1 to 2 or a 2 to 1 decimation filter. So in this example, I pump in 2 cosine waves at above and below the cutoff frequency, just so we can see that we actually decimate effectively. And we pump into the sink, out of the source, and there's no processing in between. This is all that gets plotted here. It actually does work, and it does push these samples into Vivado. So these green plots, for any FPGA developers in the crowd, they'll be quite familiar with. These are Vivado ILAs. They're essentially snapshots of the raw data on your FPGA. We can see the FIR filter on the left, and it does in fact have, a half-band roll-off. We're using about 40 taps, so it's a 40-tap FIR filter, which is way overkill for what we're doing, but it gives us about 90 dB of attenuation, which I think is more than sufficient for this proof of concept. And here's what it looks like. This is the big plot, the big aha moment. There is, on the top, we can see the 2 tones. It's reflected over the y-axis because, again, it's just real data. We are truncating, so we actually get a DC tone, which should have been resolved, but I did not get to. And we yet again take another magnitude hit, and my poorly written Python code supports about 100 megabytes or 90 megabytes per second in and 40 megabytes out. And I think this proves that it is possible, at the very least, to use PCIe, use different libraries, plop different cores in, and make FPGA acceleration happen in GNU Radio. That is most of what I have to say. All I wanted to highlight is there's a ton of work to be done. There's a ton of opportunity to kind of work together, build some libraries, build some cores, and I would be certainly happy. I've already had conversations with a few people about potential pathways and potential cores that need to be done. And I would love to find someone who's much better at software and Linux character drivers and permission structures to help. I do have a slight pitch to also mention that GNU Radio has really no knowledge of this FPGA. It's just writing and reading from it. So I have proposed just some high-level, bit-packed, information for what the version number is, what your blocks are capable of, and again, as you start to define more and more streams or more and more blocks, what they could potentially do on the FPGA. But with that, I open it up to questions and appreciate your time for listening. Yeah.
Any questions?
Thank you. Talk to me about the PCI interface that you're hooking into it. Is it a Gen 4? How many streams is it? And, are you pushing it to the limit?
Yeah, so great question. So yeah, and it's a bit of a burner to get all this in 15 minutes. But yeah, so it's PCIe Gen 2 X4, and that's a limitation from the Arctic 7 chip. Again, these were made in 2012. So they're 4 lanes. It gives you 2 gigabytes per second. Theoretically, you could saturate that link, but the Linux character driver, you're actually writing, you're physically copying the memory from user space into your character driver, and there's quite a bit of inefficiencies, especially in my code using Python. So this reference project was much closer to what I would assume the limit of the driver to be, which is close to 1 gigabyte per second. So.
Do you have in mind implementing kind of a side channel to get the metadata out of the FPGA to the driver and GNU Radio?
Sorry, what was that?
Do you have the idea of building like a side channel to get metadata from the FPGA itself into the GNU Radio?
Right, yeah, so that is the big piece of the puzzle, right? And I have some loose, kind of pipe dreams in my head about what that could be, but that's the really hard work to do. So I would love to see a couple platforms where we build out a bunch of bit files, and along with them lives JSON, YAML, or whatever type you want, and then on the actual images themselves, they have some metadata embedded in them in a predefined structure. But at this time, I just have pushed and pulled samples from GNU Radio.
Hey, Troy. Have you looked at using like the custom buffer feature or the GRC domain feature for sort of more tight integration into GNU Radio? Like, for example, it looks like if you are stringing together multiple blocks, you had like your examples, the FIR filter, but let's say you're combining that with an FFT core or something, right? Looks like they all get like put together in one big block. But would it make sense to have like a custom buffer feature where you could have that level of granularity inside GNU Radio? Have you thought about that?
Sure. So I guess I've thought about it a little bit, and we can also take a much longer conversation offline as well too. But so I have not thought of the GRC like predefined memory, because that solves the double copy problem, right, is what you're trying to address. Right. I have not, and that's the big limitation right now is we're copying memory out, putting them to block. I think one advantage, and Derek and I were having a conversation about it, is I think to make it approachable to hobbyists and enthusiasts, I think one strong advantage of a cheap FPGA is you can't do gigantic hundreds of blocks in a design. So the simpler we make them, the easier it would be, but there's also some, Derek was explaining some pathways to actually compile VHDL or HDL in GNU Radio. So long story short, I have not looked into it, but I would love to explore those options and kind of hear some pathways, so, yeah.
Do we have any other questions? Let's thank our speaker one more time.
Thank you.
Our next speaker is going to be Paul David talking about powering cognitive radios with LLM.
Perspective GNU Radio. So let's get started here. So the agenda, I just wanted to figure out a way to use LLMs to generate flow graphs. Or in this case, use them with GNU Radio. And so that's sort of the first part of this talk. The second part of this talk is sort of continuing my AI journey into a different type of model that I found along the way. And so the motivation was, initially was, how do I use LLMs to control radio systems? GNU Radio seemed like sort of a natural choice for this. So at a high level, I wanted to use LLMs to either generate flow graphs or control radio systems through text to speech, or speech to text rather. And LLMs are known for, I mean, they're language models, so of course they work best for language type tasks or structured text. But they're, like all deep learning, fairly slow, right? Like the training regime is different than the inference regime, but you have to have a decent machine, a decent GPU to really train these things. And then on the inference side, you still need quite a bit of compute. There are examples where you don't, right? Like YOLO is pretty fast on embedded machines, but the rule tends to be that deep learning is deep, right? It's heavy. So that led me to a separate model that I'll present here for the first time. And it's based not on deep learning, and I've managed to avoid back propagation as well. And this leads to another question, like, are there more models out there that we're just not exploring? Like, deep learning is not all there is to AI. So LLMs are typically based on the transformer architecture. They're not entirely. There were LSTMs before them, and there's sequential models that exist. And there's actually newer models now, state space models that exist. But they're deep learning feed-forward networks, so there's no feedback. Actually, some of the earlier examples did have feedback. And they're great at natural language, right? They were originally developed for language translation. So it makes sense to use them in natural language tasks. I won't go into basically because there's different ways to form an LLM architecture. I won't go into every example here, but they're token predictors, right? You have some function. It takes some input parameters and some input data, and it predicts your next token. So one of the cool things about LLMs is the fine-tuning process. So you actually don't need to train one from scratch. You can use what's called LoRa, not to be confused with the waveform. And so you can train low-rank matrices, or you can find these low-rank matrices, because the intuition being that once you've trained a foundation model on all this data, there are not too many directions that you have to train for in the weight space for newer data. So you can, instead of training that base weight matrix W0, you can train two low-rank matrices, or you can find two low-rank matrices that have far fewer parameters that you have to find. Usually, in a lot of cases, like 1% of the total model. And you can keep the base weights frozen. So it's really cool because it's much cheaper. You can do this on a single machine, single GPU, depending on your problem. And it's definitely a pretty cool finding. I think Microsoft found this originally. And there's another version of it called QLoRa, which quantizes the base model so that you don't need to load everything, like a huge amount of data into memory. For training, you can load the base weights in such a way that you can reduce your VRAM usage and really fit it onto consumer hardware, for example, like gaming GPUs. And in my case, I used 4-bit normalized floating point precision. So, I was able to get this to work on a 2070, for example, which isn't that, it's pretty old. So I open sourced this, but I developed basically a framework or a pipeline where you can train your own deep learning model based on one of the Quinn models is what I used. And I was able to get it to generate pretty consistently flow graphs. And I also provide the pipeline for generating the data, and I'll go into that a little bit more. But the whole data set's just like a proof of concept, where you can develop your own GNU radio model that hopefully can do flow graph generation and control. So an example, create a new flow graph with the ID derp, and then these are the type of prompts you would give it. And then on the control side, set the center frequency to 90 megahertz, and hopefully, it would actually control the flow graph in the right way and not hallucinate something. And so this is the CLI that I made for it, and just to test it out, and I was able to get it to generate valid flow graphs. So this is in inference mode. So you load up the model to actually test it in this little application. So there is a decent amount of data. I mean, you need a decent amount of data to train these things. It's not, it's pretty, like it's always harder. The hardest problem in deep learning seems to be the data, usually, not the architectures. And so how do we get more data for generating flow graphs and controlling them? And it's sort of natural, like, well, we already have a tool where we can easily generate flow graphs and you know, control them, GRC. So I created like this tool to just hook into GRC at different levels and produce these traces, and a separate tool that will like actually take that data and produce prompt context pairs. And you're able to generate a decent amount of data this way, actually, with just reasonable usage of GRC. So there's two loggers. There's actually one that operates at the model in GRC, like because there's a model that actually exists at flow graph construction time. But then I also hook the run command function. Like when you actually go to run the flow graph, you want that data too and those traces. So the other part of it hooks, instead of returning the run command that it normally does, it returns one that's patched, where my second logger runs. So yeah, so like this is cool, it's a good proof of concept, but there's a lot more to do. Like the more diversity you have in your prompts, obviously the better it's going to follow your instructions. This is originally built on the Quinn model, so it already had sort of a basis for language. So it was pretty good about like replacing the right fields in the flow graphs and actually like doing the right thing. But every now and then, mostly because of the limited data I produced, it would hallucinate a block that didn't exist. But I mean, it would still generate valid flow graphs, which I thought was pretty impressive. So this is the part that's pretty new, and it was kind of a journey, right? Because I started with LLMs and deep learning, and I'm sort of dissatisfied with the fact that you need a separate training regime, and it's very different from the inference regime that you operate in. So I went down the rabbit hole of cellular automatas and was able to find a model that I don't think actually exists anywhere. I couldn't find it in the literature, where you embed a neural network into a cellular automata. And if you could do this, of course, cellular automatas are very, very, very computationally efficient. You don't even need CUDA to run these things. Just run them in like a fragment shader. So that was sort of the motivation. So they were originally discovered by von Neumann and Ulam at Los Alamos for the purpose of like trying to create a universal constructor, which was like a self-replicating machine. And one reason they're so efficient is because they follow these local rules, and they don't. I mean, it's not strictly required that they follow local rules, but typically they follow these local discrete update rules. They're like more general examples of like iterative maps. And so this really comes from a subject called dynamical systems. And so it's really sort of a rich area to study. So I thought it was pretty cool to get into. And we all know, I think a lot of us know Conway's Game of Life. Like that's sort of the popular example. Sort of the rich dynamics you get in these simulations with really simple rules, right? So this network is, so I was trying to shoehorn a neural network into a cellular automata. There's not really a good way to, find rules for cellular automatas because they generally resist prediction, which is another cool aspect of them actually. But you know, in order to evaluate the fastest way to sort of predict what a cellular automata is going to do is by running it. So there's a lot of efforts into like searching for rules in this space. And so one idea is to introduce a neural network into one that doesn't need backpropagation. So how would you do that, right? In neuroscience, there's this idea of that cells that wire together, or cells that fire together wire together, which I think is more of a statistical statement. Cells that typically fire together should wire together. And so in my model, I keep it discrete. It doesn't have to be discrete, actually, but it makes the analysis easier. And so like activations are like spins, so they can be -1, +1. The weights can be -1, 0 for inhibiting, and 0 for no connection, and +1 for a connection. And then I added an extra mechanism, like a feedback mechanism for actually getting it to do a task called modulation. And so that's just an external field on the grid that diffuses locally. And so each cell is doing this correlation statistic as well. So there's these other parameters called traces, where you're trying to figure out for a connection, like how, what's the correlation of two cells like firing. And so this is just like a raw correlation metric. And so these are all the ingredients to this model. So I already sort of answered how we might avoid backpropagation. Is it possible? And in this case, the modulation field is the solution, right? And so I designate one cell to be that sort of feedback cell, that readout cell, and that diffuses the feedback outwards to all the other cells. So this is sort of this is like a 3-factor update rule to the weights. So weights, so the delta W there, it takes into account that correlation metric, and then that modulation value that actually should be thresholded. The correlation metric should be thresholded if you want this to stay within -1, +1. But without sort of this feedback, the Hebbian learning is not usually stable. So in a lot of neuroscience models, they don't really evaluate them for, they're not trying to build like a model to learn in a practical sense. So even with this feedback, like how do you diffuse it, right? Even with this feedback, I couldn't, like initially this model wasn't stable. And by adding, it actually turns out that the field diffusion is important for building connections, because this is a fully recurrent network, right? What if you get two symmetric connections and you get oscillations and you can't get information to flow in this? So one idea is to add a direction indicator. So like, basically you can tell if you keep a counter of when the wave hit, you can tell what direction that modulation wave came from. And then you can make your weight updates based on that. So that sort of builds almost like a directional graph into your cellular automata, so that you encourage information to flow to the readout cell in this case. And this is what it's a flood. So the strategy for diffusion could differ, right? But in my case, I used a flood. So like my readout cell will actually isotropically expand, right? So, and then your counters will increment as it does. And so you can see sort of in this plot, your outer edge of your grid is going to have the highest count. So this is actually the more correct update, the weight update function. You usually threshold the correlation value at 0. So if your correlation is positive, the output of that would be +1, the f of theta, and then if it's negative, it would be -1. So this is your update rule, and then you apply it to the weights pretty simply with clipping. So very simple computationally. So I kind of naturally, sort of a natural application is just like modulation classification. Can you tell from a constellation can you create like a PSK classifier? And so you, sort of the regime that you train this in is you implant the image into part of the grid. In this case, it's 32 by 32. And then you choose some cell outside of that, right, because you don't want it to be in your implant region. In this case, that bottom cell, it's like kind of highlighted in red and has an R on it. That's my readout cell. And then you run the network for some number of ticks, like 30, 50 ticks, or time steps, and you read out the result. And then, of course, that's like, that tells you, in this case, the target class is BPSK. So +1 corresponds to white, -1 corresponds to black. So, you know, we get the +1 in this case, and if it gets it wrong, you would send that modulation out, and every cell would update its weights. If it gets it right, I just generally don't diffuse anything from the readout cell. So in this case, it gets it right. It's already trained on, I think it takes something like 20, 30 iterations on very simple problems. It's still sort of, I'm still in the exploratory phase with this. So I'm trying to figure out, like, I need to run it on benchmarks, of course, and here's QPSK, in which case it should output black for the readout cell. So you can see, it's actually a one versus all sort of classifier. So you choose a target class, and then it outputs white for that, and then for all others, you can get it to output black. So it's not a binary classifier, it's, I think they call it OVA. And so it actually, like, once you get these things trained, it's very sort of clear that it's like forming these attractors over time. So even with noise and perturbations, it does pretty well. It still will get the correct classifications. Again, I need to actually run it against MNIST and CFAR and some standard benchmarks to get some performance metrics, but there seems to be a denoising sort of characteristic to it where it sort of converges to certain outputs. And so I didn't describe this picture. The first half is like time 0, and then the second half is like 30 time steps in, and that's your result, right? And so it looks kind of chaotic, but with cellular automata, it actually turns out the more interesting things happen in this sort of region where it's, they call it the edge of chaos, but so some of the more interesting cellular automatas happen in that sort of regime. I think I'm still exploring this part of it too, but I found some connections to like energy models. I think this is very reminiscent. I think it's called the Ising model. And so these are sort of physics-based neural network models, right, that have existed before this. And like a good example is like a Boltzmann machine. Hopfield network is probably closer in spirit to this. But they're all examples of like networks that have energy functions. And so I think there's some mathematics worth exploring here that I'm still going over before I present. But so yeah, like I said before, still need to evaluate this on standard benchmarks. If this works and it scales well, computationally, it's awesome for like DSP and data flow networks because it can just run, right, every time step. You don't need to have the separate training versus inference phase. And yeah, I'd like to put it like a PSK classifier into a GNU radio block as well, so that's sort of the next step. So yeah, LLMs are awesome, and that started my journey, but there's other models out there, right? They're not the only type of machine learning or AI model. And I think it's worth exploring some alternatives that are more biologically inspired too, and better suited for like communications and like a data flow, like DSP kept regime, because it'd be awesome to have like, for example, a neural network that could learn to be an oscillator, right, or do something more interesting really quickly. So I don't know if do I have time? Am I good on time? Okay. Maybe I can get my, this is difficult. Hold on. So, I don't know how well you can see that, but let me just. So I'll start like, this is sort of a program I developed so I can visualize the network learning and converging. I would show you the actual network. That grid was the network, but it's like very hard to interpret because of how fast it moves through the time steps. But I'm just showing it different patterns, and then eventually, after usually like 40 to 50 iterations, unless the demo demons hit, you'll see those weights. That bottom right plot there is sort of the weight space, and you'll see that stop updating, and the errors go to 0. In this case, the target class, I think, is the BPSK-like pattern. But yeah, that's sort of, it's of course going to give me problems right when I need it to. There's some bugs in this program. I have benchmarks that are much more certain, but I tried to put together a live demo here. I might have started in a bad state as well, so it's not, I couldn't really see the interface there, but. Yeah, I might give up here because I can't really see my screen. Anyway, if you want to see it later, I can show it off. But yeah, that's it. Any questions?
Hi. You pointed out in the first lines that basically quality data supply is critical for this research. Do you think that IQ Radar based database with the community supplying samples with the metadata, clearly specifying what the capture was, would help you?
I'm sorry, I really couldn't hear the.
Do you think that if community will create IQ engine-based database and community members will just dump, samples with the metadata, will it help in your research? As a, data intake?
Yeah, I think so. Like, if I understand, are you talking about the LLM or the Hebbian one?
It would be IQ data with the metadata.
Yeah.
Samples.
Yeah,
because more data, more more precise, more, and you can try just different models, different.
Yeah, I do think the more data is better. I think in the case of the LLM, I was doing more text generation and flow graph generation. So in that case, the data is just like flow graph, like traces of flow graph activity, like when you're adding a block or making a change to the flow graph. So I'm using the LLM more in a text generation type problem. But for the Hebbian stuff, yeah, that I'm trying to apply at a lower level to like sample-based problems, like problems that would run in a flow graph, right? Like you can imagine running that classifier sort of like it's fast enough that it could keep up with a flow graph in like raw samples. So that's sort of more lower level. I don't know if I answered your question, but yeah, IQ data would be for the second model. I would definitely use that or need it.
All right, thank you. Okay, let's thank our speaker. Next up is going to be John Malsbury from AnySignal.
from our early break. Sorry for the little bit of mix-up. First up, for the lightning talks, we have Carlo talking for Mona Timms.
Hello. Okay, hello everybody. I'm Carlo Manfredini from Sydney, Australia. I'm one of the co-founders of Mona Timms. And basically, I'll just tell you who we are and what we do, and then I'll say why we're here. So back in 1970, a telecommunications professor at Uni of New South Wales wanted to teach telecoms and not electronics. He didn't want to fiddle around with electronics in the telecoms lab. So he thought the best way to teach telecoms was to approach it at the block diagram level. So at the block diagram level, you'll see over there a very familiar QPSK equation, multipliers and adders, etc., etc. So basically he thought, if I make an individual card that plugs into a rack, a little bit like this, plugs into an EU rack with some electronics on it, I can build the mathematics of very many telecommunication systems. So just like Lego, if you buy a bunch of blocks and patch them together, you can make a house, then you disassemble it, and you can make a car, then disassemble it, you make a dinosaur. Using an array of individual hardware blocks, he was able to build, very many telecoms experiments. In 1986, he approached my friend and I to commercialize the product, and since 1988, we've been manufacturing and exporting all around the world. So we're basically exporting the block diagram approach. That's the core part of how we teach telecommunications. And it's very similar to the way GNU Radio works and the way LabVIEW works. You patch together blocks to build a mathematical system, basically. So with that system, the really issue is to help students understand what's going on with amplitude, phase, and frequency in modulation. So using this system, a combination of analog and digital blocks, you're able to patch together really basics like amplitude modulation, phase, frequency, and then you're able to include decoder blocks and modulators so you can start to get into BPSK and QPSK. And then if you're throwing some convolutional blocks, you can do convolution and Viterbi. And then we have a few more blocks so you can do spread spectrum and spread spectrum, OFDM, and so on it goes. It's a very large suite of experiments. So I guess the question is why are we here at this particular conference? So, in the transmission model, you'll start off with encoding and modulation and then hardware and demodulation and decoding. And with software-defined radio, now that's taken over some of those parts of the transmission model. So what we thought was very interesting for students was to not only have hardware, real signals, implementing DSP or implementing, fundamental mathematical blocks, but we've created our own individual card which interacts with GNU Radio. And it basically is simply 4 analog inputs, 4 analog outputs, 4 digital inputs and 4 digital outputs, all sampled at 48 kilosamples per second. And we have our own out-of-tree block, sync and source, and a variety of other blocks. So we're going to be putting that stuff on GitHub so people can explore what's going on. But as a consequence of doing that, because we're educators, when people have their own blocks and they introduce this module into one element of their experiment, we've created a manual which ships with that module. And so to give you an idea of what we actually kind of do, how we get students to comprehend software-defined radio versus, just the trigonometric AM and FM and that kind of thing, is we first of all introduce what's I and Q modulation about. Then we show the students, we give them an experiment where they actually build AM, DSB, Armstrong's phase modulator, FM, using I and Q modulation. So this is actually a pretty big leap for, introductory undergraduate students to go from manipulating sinusoids to suddenly creating these magical IQ signals which when mixed up to passband create the scheme that they've just been studying a couple of weeks ago with discrete modules, is really interesting and is a bit of a change of mindset. Because at the end of the day, software-defined radio is blocks of data which are moving about asynchronously or synchronously, but regular analog and digital processing is all continuous signals. So that's the leap, the hurdle that we aim to address with our modules and with our documentation. Later on, we cover BPSK, QPSK, etc., GMSK, FDM, and then we start to introduce IFFTs and FFTs. So we're providing, the way we're getting this across to students and professors who are not familiar with GNU Radio, is we're providing GRC code so that they can just bring it up, patch together the experiment, and then start to see the similarities and the differences, benefits and disadvantages of working, in the software domain. And then finally, we start to explore OFDM. Equalization is a fascinating topic. We actually are producing a three-dimensional phasor plot GUI, which we'll share on GitHub. And what's really nice about that is we can show the test vectors, how they get distorted as they travel through the channel. And it's very easy for students to comprehend that equalization is basically just realigning those vectors. And then finally, we address some radar topics. So basically, we only operate at the physical and the data layer of the OSI model. We don't get involved in protocols or anything like that. I guess another really important educational aspect is because we don't want students and professors to be hassled with installing Linux and GNU Radio, our product ships on a USB stick. So basically we have Linux Mint and GNU Radio 3.10 perhaps on a stick, and they just simply boot from the USB. So the solution is, if they have our equipment already, either our big platform or our small platform, they simply boot from the USB stick, up comes Linux Mint, it's got a built-in oscilloscope, all that, they run it, and then they simply plug into the module and pull up our out-of-tree blocks, which are already there, and they're up and running. And I guess the only thing I haven't really addressed is how do we handle the passband? It's an educational system, so our passband is at 100 kilohertz. We specifically use 100 kilohertz because we want students to be able to zoom in on a regular scope and actually see the carrier get manipulated in real time with a baseband. So if you're doing, say, phase shifting or some phase BPSK or QPSK, you can look at the baseband I and Q signal, you can look at the carrier and see it flipping at the transitions. Things like that, principles like that are possible at 100K. They're not possible at many gigahertz. And so that's why our teaching system is around 100K. Of course, we have some users around the world who actually grab the signals at 100K and then bounce them off a satellite and bring them back down again. It's open architecture. So basically, think about the TIMS product. TIMS stands for Telecommunication Instructional Modeling System. Think about it as basically a bunch of hardware and software elements like Lego that allow you to basically, teach what you want to teach to your students, as well as make your own modules, etc. And you can find us at qpsk.com. I'm very amused to say that we bought that domain back in '96. We were thinking, what's a real cool domain? And AM was taken and FM was taken. And QPSK was just starting to be a thing in 1996, so we bought it. So, and I think that's probably my time, is it? Awesome. Any questions? I have a question. How come simulation hasn't destroyed us already? 20 years ago, when simulation came out, we thought we were dead. But it turns out professors are giving us feedback that students don't learn when they purely use simulation. And so they really need to use that intuitive hands-on approach. Right.
All right, well,
All right.
let's give a round of applause for Carlo. And up next is Steve with his Linux handy talkie portable SDR transceiver. All right, so we're going to do a slight switch.
I hope this works. Ta-da. Okay. I bring you greetings from the world of amateur radio, and we have, oops. I bring you greetings from the world of amateur radio, and we have met you at your required hardware. This is a project that is new this year, actually in the last few months. LinHT, Linux Handy Talkie. And we've tried this before of doing a full SDR in a handheld portable version, most specifically about 10 years ago. Is this a 15-minute slot? 5 minutes, okay, I'll be fist. So we're trying it again with new people, new technology. I'm told there's 2 ARM cores and an FPGA on this, or sorry, 2 ARM cores and a radio chip. Easier to program, and this is not my presentation. This was presented last week last weekend for the first time. This is the actual unit. They took an interesting approach that they took the physical form factor of the circuit board in a commodity portable radio from China, and then put their own circuitry on it, slapped it in, a few donor components. This is still very much experimental. There's the SPICs. And the cool part is it runs GNU radio right on the radio. You just load your flow graph in, boom, done. We think this is going to be a very big deal. And we think that the Chinese manufacturers, once they get over the who's going to be first hurdle, are going to be very interested in this because they'll be able to push this radio out certified as DMR or FM, and then, okay, fine. Community, you support it. All the weird stuff, you support it. I'm just going to fly through these a few. So this is very early days. They have only a few of these prototypes done, but they have been proven out. It works and it runs Doom. Okay, so let's see. Where is the other bit? There. Okay. First test. So if you want more information, m17project.org. They have a blog. You can get more involved. This is sponsored by the M17 Foundation. This work is currently being all done in Europe. M17 Foundation is based in Poland. So lots of fun. Any very brief questions?
All right, thank you. Yeah, we actually have time for at least one question from the audience. Does anyone have any questions for Steve?
Yes, m17project.org, and the organization is m17foundation.org.
Hey, Steve, what was the time frame again for these things being able to be ordered in any kind of quantity?
No idea. That is entirely dependent on the Chinese manufacturers getting on board and doing their own. They're not going to be, the amateurs are building these purely as prototypes, proof of concept. Then it's up to the Chinese. We hope that the Chinese will bite, but we've had some serious expressions of interest. I am on the advisory committee for the M17 Foundation.
Is this an open hardware thing where
It
the
is.
stuff's all out there,
Absolutely.
so I could go buy some stuff and build one?
That is the definition of M17. It is the first totally open source digital voice in amateur radio, designed by amateurs, for amateurs, entirely open source. It ain't perfect, but it works.
All right, Steve, thank you very much. A round of applause. Up next is Martin, who will be talking about GRC-based RF NOC workflows. That's a good point. There are still ham radio exams going on if you want a chance. There's probably still a chance for you to go take it. So once again, encourage. Ready, Martin?
All right. So this is something I put in as a lightning talk. Go away. Briefly, just recently, because I don't know. I didn't have it in my earlier presentations. I thought this might be interesting. So when we do anything with GNU Radio, with from NI, Edis Research, Emerson, then we try and be good citizens, upstream everything, etc. And a cool feature that we've been working on that has been available for a while now is the domain concept in GNU Radio Companion and the alternative workflow concept. And I thought I'd just quickly show them because it's kind of neat. So we've been doing a lot of work with RF NOC tooling the last couple of years. So RF NOC is our framework for deploying arbitrary IP on USIPs, and you have to have a way to define like which IP blocks do you want to have. Like, do you want to have an FFT or whatever? And one of the workflows that we have is this GNU Radio Companion-based workflow. So I'm going to zoom out here. So this is not a flow graph. This is like an input for an FPGA build process. So I can take this now on this laptop. I cannot do this. It does not run Vivado, etc. But if I had everything installed, I could like click play, and then it would actually start compiling this down to a bit file. So what's going on here? So every block in here represents a signal processing component on the FPGA. So I can zoom in a little bit. Sorry, this is not the ideal screen resolution. Come on. Yep. Go faster. So for example, here I have an RF NOC radio block, which is an RF NOC block that, well, like it says, controls the radio. And then there's a DUC, a digital up converter. This is a resampler and a digital down converter. And then I connect them in the fashion that I want to have them, connected when they're on the FPGA. There's this mega block here called the DSP block. This is what provides all the clocks and whatnot, like the features that come from the device itself. So you have to select what device you have. In this case, it's an X310. You can say, like, do I want to have DRAM support and whatnot. Other devices have more features, like, for example, here the X410. This is a bit more beefy. You can see, like, I have all of these QSFP adapters that may or may not be connected to an Ethernet transport. But it's the same principle. So this is, you can see, like, I have all of these differently colored arrows. It can be a bit confusing, but that's just because there's so much going on in here, especially, like, I have to connect a lot of clocks. And one of the reasons we did this was because we already had a workflow where you can run combined RF NOC and GNU Radio applications from GRC, and I think this is also pretty neat. Now again, I can't run this, I don't have any hardware attached, but you can see here I have an FFT block that's running on the FPGA, connected to a bunch of other blocks, so FIR filter in this case, and another FFT block, so this, oh yeah, exactly. This is an OFDM example. So we send OFDM data that we generate with like the OFDM blocks in GNU Radio into the FPGA. We do an FFT with cyclic, sorry, I guess it's an IFFT with cyclic prefix insertion. This is sort of like a channel model, and then we turn it back into symbols, and then we can sort of look at the the OFDM symbols after they've went through a channel, like all in the FPGA. So this is a program that if I had the correct hardware attached, I could just hit play, and then it would like run like a combination of GNU Radio blocks and FPGA blocks in a way that I think is pretty intuitive. And yeah, and that's why we added this workflow as well, because we kind of didn't want to have to leave GNU Radio even for the FPGA bit file compilation. Of course, this does require Vivado and UHD in the background, but the main reason I wanted to show you this is became obvious to me this week that people aren't aware of these features that are now in GNU Radio. And Derek was saying that the Casper project has made use of this for something. I haven't really seen what exactly, but yeah, it's something that you can use, so feel free to use it, but you can also use it for RFNOC, which would also make us very happy. Okay, that's it.
All right. Thank you, Martin. Next up, we have a raffle, I believe.
Yeah, that's also me.
All right.
I just need to grab the stuff, one sec. Actually, Kelsey, can you, thank you very much. So, I need a volunteer to help me with the raffle. So, anyone? You? Okay, perfect. You, just by being the volunteer, you already get a prize. Because yes, we have prizes, and one of the prizes is going to be a USAP. So, you're not getting the USAP just for helping, but you might get one. So yeah, we need to get prizes. If you're not in the room, you're not getting the prize. I'm not running around the conference tracking down people or mailing prizes. I'm just going to pull names out of this box until someone raises their hand. All right. Okay. Shall we start with the cheap prizes, or shall we start with the USAP? Let's do USAP last. Okay. So, if you pull your own name, that's fine. So the first we have a backpack. So do you mind? Thank you. So the backpack will go to Christina Rivera. I guess not. Need a new name, please? All right. Zachary Hicks.
All right, thank you. My name is Soham. I work as a wireless systems engineer at Skylo Tech. Today I'll be presenting about a passion project of mine, and this is about tracking whales, marine animals, blue whales, and the technique that we do to study these animals is we add a tag on top of them, and these tags contain sensors. These sensors could be IMU sensors, cameras, and heartbeat monitoring sensors, and GPS as well. So what happens is we want to study these animals for their different behaviors, how large they can get, their feeding patterns, their migratory patterns, and how it changes related to changes in the environment, changes in the water temperature, and climate behavior changes. So one of the important informations that we require for such a project is the location. And obviously there is no GPS underwater so far, and but the good thing is that these whales come up to breathe, and when they come up to breathe, it's usually, depending on which breed they are, it's typically 3 to 5 seconds. So a typical GPS log can take much longer sometimes, so the normal GPS solutions do not work. This is just a cool example of how one of these tags look. This is a dolphin, and these are the IMU sensors on top of it. And let me show you how they actually put in the tags on these whales. So somebody actually takes a boat, they go there and they put it on the whales. It uses suction pumps to stay on, and then after the mission ends, somebody goes out and retrieves these. So we get a lot of information from these tags related to depth, and if you can see here, the surfacing intervals are very short most of the times. This is still a good example of it going up to 10 seconds, but typically for some breeds it's less than 3 seconds. So the idea is to have a GPS alternative way using software-defined radios to track and monitor these marine animals. And this is a very, very simple diagram showcasing how such a solution could work. And we will be using amateur frequencies, and the power ranges could be depending on the frequency we use. Could be 50 watts to 1.5 kilowatts. And the target is to track them over 50 to 100 miles, and precision requirements of 50 to 60 meters typically. Some of these blue whales can go up to 30 meters. So it's a very simple example of what needs to be done. Actively looking for ideas and suggestions and collaboration opportunities. So if you're interested in helping out in tracking these marine animals and working on some interesting blue whales and dolphins, I'll be very interested to hearing from you. This is my email address, and if there are any questions, I'll be happy to take them.
I think we have time for one question from the audience. All right. Hold on.
Yes, so.
Do you want to repeat the question?
Yeah, I can repeat the question he asked. So he just asked about dead reckoning and whether we can actually use some of maybe one GPS log and then track where the whales are going or the sharks are going at certain points. So that's exactly the idea. So these whales or marine animals, they surface for a few seconds, and then we will be using those logs and then using dead reckoning to actually track them in the whole, in between the surfacings. So yes.
All right. Well, thank you very much.
Okay, thank you.
Now we're time for break. And also I should mention we do have a workshop this afternoon, USRP FPGA processing using the RF NOC framework.
Yeah, it's super pretentious title, I have to admit. And with a title like that, I'm sure you're expecting like these amazing insights, like this fundamental, like this is like the last talk you'll ever need to listen to when it comes to streaming over Ethernet. But the truth is, I sort of was like researching this and I kept running into walls. I also ran out of time, so I thought instead of giving you this like amazing, like be all end all presentation, I'll just rant about something. So I thought, so this block here, I don't know who's used the UDP source block. It's like, it's not very good. At least that's what my first impression was. You know, the performance is not good. It has weird requirements when it comes to packet sizes. But then I thought, I can't just go on stage and rant about a blog, especially someone's put a lot of work into that. And to be honest, it actually has a lot of things going for itself as well. So the portability of this block is really good. Works across, you know, IPv4, IPv6, all sorts of operating systems. But, you know, all of the advantages, I'm going to ignore them for a sec. I'm just going to, like, this block has some disadvantages, and that's what I want to talk to you about. Okay, so what's the problem? So the performance of this block, like I said, is not very good when it comes to just raw throughput. Now, how do you even measure that? One way to do that would be to, okay, actually, need to step back a sec. So we're talking about UDP streaming here. When you do UDP and your network can't keep up, packets will get dropped. Yeah, that's how UDP works. So back to where I was earlier, one thing you could do is you could sort of slowly crank up the speed of a streaming interface and see how fast you can go before your computer starts throwing away packets. So that would be one way to do that. I flipped it around and I said, no, I'm going to use a fixed data rate source. In this case, I used a USRP X310 because I just had one around. And I set it to its own maximum rate, which is 200 megasamples, which is 800 megabytes. And with 200 megasamples, it gives you about 2,000 samples per packet. So it has like 100,000 samples, UDP packets per second at a very accurate clock rate that sort of interval that'll reach your computer. So instead of saying, how fast can I go? I said, given this speed, how many packets can I successfully receive? And there's a little block that I wrote, and it's called benchmark. Again, it's a bit of a pretentious title. All it does is count the number of samples that it successfully receives. So on my computer, which isn't super new, but it's also not super old, Intel i7, 3.5 gigahertz, I can successfully receive somewhere between 4 and 8% of all incoming packets, depending on how I tune my network settings. It's not great. And that's where my dissatisfaction with the block comes from. So you might say, well, can you do better than that? And I gave it a shot. First try, 50% success rate with this block here. I pushed this all onto this GitHub repo in case you're interested. But for the next section, I want to talk a little bit about the background of network programming and see, you know, what did I have to do to get there? Also some basics, you know, just some fundamentals here. You know, I usually come to GRCon and give a talk about some fundamentals of something like DSP topic, so I'm going to put this back in here. Okay, so how do you do network programming? So there's the lowest level API that all operating systems offer is the socket API. So I'm sure this is something you're all familiar with, or at least you've heard of it. To use the socket API on any POSIX compliant operating system, you have to do three things. First of all, you create the socket itself. And when you create the socket, you're already telling the operating system what kind of socket this is. So datagram, UDP, so this is a UDP socket. And a socket is a file, essentially, so the return value of this function is a number, which is the file descriptor that you're going to use for the UDP streaming later. That's going to be relevant later. Next, I take this newly created socket and bind it to a port. So these APIs are great because they're easy to use, and I think they're also pretty intuitive. So bind, you just say, hey, I bind this socket to this address, and the address contains an IP address and a port number, and once that works, you can then start sending or receiving data. And if you want to send data, you call send, and if you want to receive data, you call receive. It's really, really straightforward. So what's the problem? Is that something we should just be using? There's like a bunch of problems with this. Like portability aside, this is very system call intensive. So this is something, I have a longer version of this presentation where I go a lot into system calls. I'm gonna have to cut that out just for reasons of running out of time otherwise, but I think you're probably familiar with the concept. If you do a lot of system calls, you're switching in and out of like application space into kernel space and back. That's not good. But the other problem is that this function call, receive, is a blocking call. And that's not allowed in applications like GNU Radio. I can't just hang indefinitely. So if I call this, but there's no actual traffic on the network interface, this function will simply never return until it receives some kind of signal, like imagine you control seeing your program. That's not useful. So I need a way around that. And to unblock my receive operation, there's a couple of things that I can do. First of all, I can just simply pass a flag into the receive call that tells it not to block. So the message don't wait flag. And in that case, if there's no data, the receive call will immediately return with an error code. Now, I also get legitimate error codes if there's like, network interface is broken or something like that. So I'm gonna have to look at the return value, see, is it an error code that means there was simply no data available? In that case, I'm safe, I can keep going. Otherwise, I'm gonna have to handle the error. So this while loop here is effectively, well, the way I wrote it, it's still blocking because it's not going to exit the while loop until I have data. I could like add stuff in there though that gives me a timeout or something like that. So this would be compatible with GNU Radio, for example. But I'm calling like this receive system call all the time. Now there's actually a slightly better way to do this, which is to modify the socket itself to become non-blocking. You call this fcontrol or fcntl function. It has the same effect as supplying the flag, but it actually, this is actually the preferred way to do it because it's more compatible with certain applications. Has the same problems though. So I'm still doing all these system calls, and that's not good. So then the other thing I have to do is actually, I just need to test my socket and see if there's data available before I actually pull it out with the receive call. Okay? So this is just networking fundamentals still. If I'm on a Linux system, I have 3 ways of doing that. The first, most portable and oldest solution is called select. So up top here, I basically use these macros that store the file descriptor numbers that I want to observe in this object called read FDS. And then I have this select call down here, which basically returns 1 if there is data available. That's pretty straightforward. This call has a whole suite of problems with it, and you really shouldn't be using it, but it is portable. One of the main problems is that the maximum number of file descriptor, so the file descriptor is a number, but the biggest number that this select call can test is 1023, or 1024. No, it's got to be 1023. So, but what if you got a bigger file descriptor number? Well, then you're SOL. Like, it's not good. So this is like old, and there's a better way to do that, which is called poll. It's also a much cleaner, simpler API. The concepts are the same. I declare all of the file descriptors that I want to observe. In this case, it's only 1. And then I call poll with a timeout. And the way this works is, and then this is also true for select, I call this on my file descriptor. If there is data available, it'll just return 1. If there is no data available ever, it'll eventually return 0 after a timeout. And during this timeout, if there is incoming data, then it'll also return 1, but it'll stall my thread. So the thread execution is halted, which means I'm also not using any CPU cycles. I'm still switching into the kernel though for that. But I'm not doing it all the time, so at least my CPU utilization is much improved. So there's a third API on Linux, and this is Linux only. This is completely unportable. That said, anyone that's doing high-performance network programming is using Linux anyway, so it's not a big deal. But still, epoll is like the current state of the art for this particular problem. You can see it's already like, just by the amount of code, it's much more complicated because it has more options. And it has 2 advantages over poll. The first one is that it's much faster. So poll and select actually scale within O of n, where n is the number of open file descriptors. So if I have lots and lots of ports going on, poll and select will get slower and slower, whereas epoll does not. So it's faster. And the second thing, which is also a minor performance improvement, is it can be used in an edge trigger mode. So the edge trigger mode is something I need to explain. Imagine I have data incoming, you know, and some socket buffer is accumulating data. So data. And at some point then I say, okay, I'm going to drain the data, so there's none left, and then later I get more data. If I use a level triggered approach, which is what select and poll do, then I will always get a true value or a 1 value out of my select or poll calls while there is data available. Whereas this edge triggered mode will only do this once. Like when there's new data, there's a trigger, and now you go receive. And this is just also, you know, a slight performance improvement. Okay, so put this all together. I have my basic fundamentals for socket programming. Obviously, send does not have this problem. I can, I don't have to query the file descriptor for that. But there's actually much better technologies available these days that I could be using. And one of them is I/O U-ring. So I want to talk about that a little bit. I/O U-ring works as a way to do Linux system calls through a submission and completion queue. So instead of calling my system call directly, I basically put in a request for a system call into a submission queue. And I can put in as many as the size of the queue, and the kernel can then sort of pull these system call execution requests out of the ring whenever it's like a good time for the kernel, and put the result into a completion queue. And then the application can read the results out of the completion queue. And what's important is to know is that most interactions with the submission queue and the completion queue are not in fact system calls. So I do not have that system call overhead. And I'm sort of giving the kernel a little bit more space to handle all these requests. This is an example for how to do a receive call synchronously and asynchronously. So this line here is just the synchronous receive call. And here's all the code I need for the asynchronous call. So first of all, I need to actually configure these ring objects. That's what I do here. Then I need a pointer to a submission queue element and a completion queue element. I will first take the submission queue element pointer and load it with a receive call request, so prep receive. So this is the same, so these arguments here are the same arguments as to the actual receive call, but I'm just sort of loading a request for that into the ring. Submit puts it into the ring, and now I just have to wait until the kernel has actually executed it. And when that's the case, I can pull the result out of the completion queue with this call, and then the return value of the receive system call, which happened asynchronously, is now available to me through this completion queue element. So pretty nifty. This seems complicated, you know, like just like one line here versus like many lines there, but it's actually not that bad if you put it into context. So here on the left, I have a socket-based implementation. On the right, I have an I/O U-ring-based implementation for the same problem. And here on the left, I now also have to do the epoll and everything else, and like some handling. And coincidentally, it turns out to be the same number of lines of code if you remove this I/O U-ring initialization code. It's a bit of an apples to oranges comparison because the code doesn't do exactly the same thing, and it's also not proper asynchronous code on the right. This is just to show you that just because you're using I/O U-ring doesn't necessarily mean that your code gets much more complicated. But this, I mentioned already, this is not how you would program asynchronously. Like, because on the right-hand side, I'm effectively doing the same as on the left, where I'm putting in a single receive call, and then I'm waiting for the result to come back. Like, the only thing this does is this avoids doing the receive system call, but I'm replacing it with a I/O U-ring wait CQE timeout system call. So this is, I haven't won anything yet. Like, you would expect me to be filling the submission queue asynchronously to the the completion queue evaluation. So quick reminder, so that's how you have to sort of approach an asynchronous programming paradigm. So like I said, what's stopping me from just putting in, like, I want to receive as fast as I can. Remember, that was the original problem that I set out to solve. So I should be like putting in all these receive requests, like keep this here always filled so that the kernel always has like some work to do. And I could even then spread out the completion queue evaluation onto different threads or something like that. But at the very least, if I'm streaming quickly, I would never have to do a system call, you know, a switch, because like this is always full, and then this will also be full, and then I can just keep reading data out of that. So that should give me an improvement. And there's, in fact, a new feature in IOU ring that is so cool that I, you know, thought I'd give it its own slide, which is called multi-shot operation. So what this does is, it's sort of a machine gun mode for IOU ring. It says instead of putting in a single receive request, I can put in a multi-shot receive request, which is effectively me asking IOU ring to handle a receive request for any incoming UDP packet, and I only have to submit that once. So I can completely forget about the submission queue at that point. And this is an example how the actual receive would then wait. So basically here I'm waiting for a completion queue element to be available, which means there was a receive call that was executed. I do a quick check that the receive call actually worked, and then I have to do something that I don't have to do otherwise, which is to figure out where the kernel actually copied the UDP packet payload. So I have to like pull out a buffer ID out of this completion queue element, and then I need some code, which here is just B, which gives me a pointer to the actual buffer. And there's like some magic that goes into that, but it's not particularly complicated. So I provide some buffers, and the kernel just puts every incoming UDP packet automatically into a buffer. So that's pretty nifty. Here's sort of a quick overview of how such an application then looks with all the available, or all the necessary steps. So application wants to do an IOU ring based receive, submits a receive request into the submission queue, and it can keep doing that until the queue is full. The kernel, whenever it feels like doing that, pulls the submission queue entry out of this queue, executes the receive, and now comes a new thing that I've glossed over before. I need a buffer pool available that is writable and readable both by the application and the kernel. So in order for the kernel to actually execute this receive call, it'll pull a buffer out of the buffering, and when the receive call is completed within the kernel space, it'll put a notification into the completion queue, which also links to the buffer. And then when the application finally gets around to reading the completion element, it'll know which buffer to pull out of this ring, and then it can look at the buffer and handle the payload, do whatever it needs to do. In my case, I'm copying the contents to the downstream block, and then put the ring back into the buffer ring. So this only works, so if I'm not using the multi-shot operation, I have to keep filling this queue, but I also have to keep filling this buffer pool. If I'm using a multi-shot operation, then I have to read this completion queue out really quickly, so I can always be putting back buffers into this ring, and that's something that'll bite us later. The other thing that's worth pointing out here is, if you do this versus a synchronous approach, it's likely that you will have to do additional mem copies that you do not have to do with a synchronous approach. That doesn't always turn out to be a huge problem, but the reason for that is that you need this special buffering that is not a buffer pool that you can also use within your application. So I wrote a little program that does the same capture of incoming UDP data with a pure socket approach and an IOU ring approach. And this is without GNU Radio, this is like a straight up C++ program. And the results were really encouraging. I thought, oh wow, I'm really onto something here. So on the left-hand side, you can see the socket-based approach. I'm doing 200,000 system calls to capture 2 seconds worth of data coming in at 200 megasamples. And keep in mind, 200 megasamples is not really that fast, right? We are streaming 2 gigasamples or 2 by 2 gigasamples off of a USRP X440. So this should not be a problem. And it works, unsurprisingly, because like I said, it's not the massive rate. The IOU ring-based approach requires an order of magnitude fewer system calls, which is great. And now, how do I create this table? I use a tool called strace. You might have heard of it. It's a standard Linux development debugging tool. The overhead of running strace, because of all of these system calls, is so big that if I'm using the raw socket API, like this entire application took 10 seconds to capture 2 seconds worth of samples. So it wasn't even collecting contiguous sample data. so yeah, I thought this is great. Like this is like the holy grail of everything. Like this is really good. Now, if I just look at the CPU utilization of those two programs, it's also like much in favor of IOU ring, not quite so extreme. So this is without strace. I'm just looking at the CPU utilization with time, and on all metrics, the IOU ring based receiver performs better. So yeah. And final experiment that I did was I ran the receiver without there actually being any data, just to see how that would sort of affect CPU utilization. And in that case, you don't really get any advantages from the asynchronous model, because you're going to have to stall your program at some point. And I'm using IOU ring for that, but then I'm just having the same number of IOU ring based timeouts as I would have with poll or epoll. The only thing that came out of this experiment was it showed that epoll was slightly more efficient. And that was without me actually opening many ports. So epoll becomes better versus poll the more ports you have open. Okay, so I put it all together. So now I've learned stuff about sockets and IOU rings. So I put this into GNU Radio and to see how well it works. And I tried two blocks. So the first one is the UDP source that I showed in the beginning, and the second one is an IOU ring based source. And I was underwhelmed. Like the IOU ring based approach that I chose was not very good. So the multi-shot mode is not the right thing for this particular block. So I'm still not at the performance that I really want. Like I said, this year I captured about half of all incoming packets, which is still worse than I was hoping, and this was even worse than that. Yeah, and that's sort of the main results that I've gotten so far. I had intended to write more blocks that also implemented DPDK, which we use in UDP, and it does give us a performance benefit there. AFXTP, which is another Linux subsystem where you can provide rules where incoming packets are directly handed to your user space, and they do not have to go through the Linux kernel stack, which is expensive. Like if the Linux kernel has to look at the incoming UDP packet and evaluate port number and whatnot, like that is significant CPU overhead. So with AFXTP, you can set a rule where it says, okay, like this packet, like just give it straight to my application and I'll handle it. And I also have been looking into RDMA for this. Now, RDMA is not UDP exactly, it's not exactly the same, but there are many similarities. And if you can use RDMA, that means you might be able to get some benefits from the hardware acceleration that is involved in moving data. I don't have any results for this yet, though. I did do just a quick sanity check. So this 15-year-old USRP source block, if I use that, like how many packets do I lose? I don't lose any packets. I have 0 packet loss because, like I said, 200 megasamples is not a crazy high rate. Like this is obviously not a problem. So why am I having trouble with the raw UDP streaming? And I'm not 100% sure because when I say I'm not 100% sure, I don't have like the scientific rigorous experiment that proves this, but I'm pretty sure that the flow control inherent in the USRP data transfer is helping me, because the GNU Radio scheduler doesn't always let my work function operate within my whatever the source block is. So I'm not actually always able to pull data out. And especially in the multi-shot operation, every incoming packet will cause the Linux kernel to try and put that packet into one of my buffer pool buffers. And if none is available, I immediately get an error message and have to restart the whole operation. And with the flow control mechanism of UHD, I can sort of like throttle it a little bit. And the USRP does not have a lot of buffering space. It's not like I can buffer up tons of data, but it seems like I don't need to. I just need to be able to throttle it a little bit, and so to match the actual receive calls more to the time where I am actually scheduled to run the work function. Yeah, so there we go. That's sort of what I learned over the last couple of years. So at this point, my original intention was to like give you this summary of stuff that I learned and like these amazing knowledge bombs, but I really ended up with more questions than I had in the first place. So I'll share those with you instead. So I'm still not entirely sure what the right technology is to handle this kind of streaming problem. And I think there is not a single answer to that. Like, it's always very specific to the problem that you're trying to solve. So IOU ring, I think, is a useful technology. It's also pretty new. It's not like this has been around for a long time. So I think sort of the best practices are still evolving. And also the subsystem in the kernel itself is improving quite a bit. So I don't think that the multi-shot operation of IOU ring is the correct solution for this UDP source, but there are many other things where we can use it, like file sync, file source. Like those are things where you have, you're very system call heavy and you can employ IOU ring. Like I said, DPDK, RDMA, definitely interesting and something I'm still looking at. But one thing that really stumped me was like, what is the best benchmark? Like, what is the correct way to measure all of this? Like, what do I care about? And once again, there's no single answer to that. Like, I started out with like, I don't want to drop any any packets, or at least I want to drop as few packets as possible. But in other cases, you really care about CPU utilization or something like that. So yeah, flow control is useful. So maybe there's ways to incorporate that into sort of radio streaming the way that UHD already does. Yeah, there we go. I think we have like, I try and leave time for like 1 or 2 more questions if we have any, but that's sort of the total amount of whatever the opposite of knowledge is that I that I acquired over the last couple of weeks looking into this. Thank you very much.
All right. Thanks, Martin. We do have a little bit of time for questions. Any questions from the audience?
Did you try a PF ring from NTOP?
Have I tried what?
PF_ring. ntop.org?
PF ring?
Yeah.
No, I have not heard of that.
Oh, come to me,
Okay.
All right. Other questions from the audience? Oh, there are a few.
Hi. I'm just curious if you had considered things like the RPC calls, like Sun RPC, which also use UDP, but they had another protocol layer. And then there's also the real-time streaming protocols. I don't know if they have any support for that.
Yeah, there's plenty of things. So many of the RPC frameworks use TCP, and then there's like some inherent like network, like lower level, not exactly flow control, but like some throttling that goes on. If you use something like gRPC that has like a streaming mode, I haven't looked into the details, but it has some kind of flow control built in. So you typically don't lose data when you do gRPC streaming. If you do computer-to-computer gRPC streaming, you're just the maximum aggregate data that you can get will be the one that you achieve by means of flow control. And here, like I did the opposite, where I said, no, I'm not throttling anything. I'm just going to go as fast as I want, and you got to keep up with me. So yeah, those are different approaches. Also, like I was trying to avoid like any kind of handshaking, etc. And as soon as you're doing RPC, you have all sorts of protocols on top of that, which I specifically wanted to avoid.
Thank you for the good overview of IOU ring. That was helpful. You mentioned that if the shared buffer queue overflowed or overran, that was a kernel error. How do you recover from that? You said you had to restart everything?
So you can look at my code. It's not actually that problematic. Let's see if I have anything in here. I kind of don't. So if you run out of buffers here, the kernel gets a packet and it tries to put it somewhere. It'll simply give you a completion event that is an error code, and you have to handle that. And if the error was you ran out of buffers, like you get an no buffs, then you just have to. I was playing around with this multi-shot operation. You just have to resubmit a multi-shot submission queue entry, and then you start again from the beginning. It's not a big deal. It's pretty robust.
All right. Any other questions from the audience? All right, let's get a round of applause for Martin. Thank you very much. Okay. Up next is is it Tian Chang? Yep, with real-time scheduling and batching in GNU Radio for bounded response times. So while they're getting set up, I'll just, I think I mentioned earlier, TorchSig, we had to go ahead and move that to tomorrow. Hopefully the presenter will be feeling better then. And this will be our last talk for the day, but I have a feeling there's lots of conversations happening around. So I definitely encourage folks to take some time and see what else is going on. All right, go ahead.
All right, so I'm Brian Ward. I'm an assistant professor at Vanderbilt University. And today we're going to talk about how you can apply real-time concepts to have bounded response times, bounded latency, as well as guaranteed throughput in GNU Radio. My student Simon is going to be presenting some of the experimental results, but I wanted to kind of give an overview of kind of the problems that I see and my kind of vision for how we can take real-time concepts and use that and bring it into GNU Radio. So just as a disclaimer, my background is not in signal processing or RF. My background is in real-time scheduling. And so I've really enjoyed this conference this week, learned a lot, and hope that I can bring some perspectives and get your feedback on how we can take some of these ideas and extend them in ways that could be helpful for you all. So like I said, this is like coming from the real-time systems community, and we had a paper last year that won like an outstanding paper award at the Real-Time Systems Symposium, so we're going to present some of those results here as well as some new results. So I'm going to talk about the motivation here. At this point, we probably all know GNU Radio can do general purpose processors and signal processing. And in GNU Radio 3, the way this is done is each of the blocks is implemented as its own separate thread. Then there's the GNU Radio scheduler. I put the scheduler in quotes because it's not really actually doing the scheduling. What it's doing is it's communicating to the operating system what are the threads that are ready to run. And there was this paper at the GNU Radio conference a couple years ago at this point, where they identified that there's some issues here with this approach. You can't control the order blocks to run. You can't control for how long they run. You can't merge blocks into one thread. All you can do is kind of control how much is being processed in a single step. And so as someone from a real-time background, this was like a little bit of a call to arms. Like, I think I can help with this. And so what this is really saying is that a lot of this work is just best effort. If we have the CPU capacity, we're going to try and do as much as we can, try and maximize throughput. But there's no way that I can take this scheduling and say that I can provide a bound and say that here's our latency bound, or I can guarantee you that I'm going to be able to keep up with an input rate at a certain throughput level. So what I want to do is review what real-time scheduling means to me and how we can apply some of these concepts in GNU Radio. So there's a lot of different definitions of real-time. Oftentimes it's thinking about kind of just having an interactive system or seeing what's happening live. But from a real-time scheduling perspective, it's really more about having timing requirements and then being able to provably guarantee that these timing requirements are going to be satisfied. So this is really common in safety critical applications like aviation and automotive applications. In aviation in particular, you have to go to the FAA and prove to the FAA that your system is going to be correct. Both logically, it's going to do the right thing, and temporally, it's going to do the right thing at the right time. And so I think that we can apply some of those ideas here in GNU Radio to be able to provide these guarantees about latency and throughput. In order to do that, you have to have models of what it is that your workload is doing so that you can bound those behaviors. And then you have to have analysis techniques that you can apply to those models to then be able to provide those guarantees. So this means that you have to think about what's the worst case, and you design kind of for the worst case, and a lot of these kind of heuristic optimizations for throughput may not be happening because you really care about the being able to satisfy those provable requirements. So our thesis here is that a lot of this work that's been going on in the real-time community for the last 50 years is something that we can take those ideas and apply them in signal processing and GNU radio. We can't just, I don't think, take those concepts like out of the box and apply them. So we have to do some extensions, and we're going to talk about how to do that. My goal here is to be able to say, once we've taken those ideas and brought them into GNU radio, that we can have some of those benefits to be able to have bounded response times and guaranteed throughput. So what I want to do next is talk about kind of real-time basics for those who maybe aren't as familiar. I'm going to start with the earliest deadline first scheduler. So this is EDF. Basically, EDF is a pretty simple scheduler. You associate with each job or each thread a deadline. And then the scheduler, its job is to just schedule the thing that has the deadline that's the soonest. It's kind of like what my students do when they're doing their homework. They figure out, well, the physics assignment is due on this day, so that's before the writing assignment, so I'll do the physics assignment first. It's the same thing within the operating system. Now, there are some really nice results about EDF. It's been shown that it's optimal on a uniprocessor, so if you have a single processor, if anything can schedule your workload and meet those deadlines, then EDF can too. That's a really nice result. Now, when you introduce multiple processors, things are more complicated, a little more hairy, but people have shown that you can have soft real-time optimality. That is, you can say, maybe I won't meet all the deadlines, but my response times are not going to get kind of worse and worse and worse over time, provided that I'm not overutilizing the platform. So that's a nice result, and people then have extended that to look at graph-based task systems where you have dependencies between tasks, and that result still holds there. And the really nice thing about this is that Linux supports global EDF on a multiprocessor with the schedule deadline scheduling class. And so what that means is we can use this kind of out of the box. So here's just a quick example of what an EDF schedule looks like. In order to have an EDF schedule, you have to encode like what is the execution time, what is the period, how often things are happening, and then what is the deadline. So if we have one task that has an execution time of 1 and a period of 4, that means that its deadline is 4 time units away. That's the earliest of all these tasks, comparing against 5 and 7. And so it goes ahead and runs. We assume we have 2 processors here, so the next task runs also concurrently. When the first one finishes, then we can execute the third task. And this kind of just continues. All the scheduling is done based off of the deadlines. So the key questions in terms of how can we apply this in the context of GNU Radio is where are we going to, how can we take advantage of this, and how can we determine what these task parameters are? What is the execution time and what is the period? And in order to do that, like I said, we have to have these workload models to be able to apply these real-time analysis techniques. Okay, so to have a model, we have to first review what is GNU Radio doing, and then how can we model that more theoretically. So this should look familiar. It's a simple narrowband FM receiver, and it's got our blocks, and there's connections between them. And the key difference here from the previous slide is that we have these dependencies that are existing between these different blocks. Before, we just said we have these independent tasks, and we have to schedule those. Now we have dependencies. So how can we model those? Well, it turns out that there's a concept called a processing graph method. It's been around for a few decades at this point. And the idea is that you have these nodes, basically blocks in GNU Radio, and you can associate rates with them, as well as the relationships of the dependencies, and there's an assumption there's a producing and consuming of tokens or data from one node to another. So we have this source node. It is, there's data that's coming in every 1 time unit out of every 5. Then you can encode like a produce and consume relationship. So this one is consuming 10 samples and producing 1. And then if you kind of walk through this graph, you can determine what is the rate of all the subsequent blocks in the graph. So this is kind of walking through an example. The source gets some data, and then that enables the next task to run, and it does this over and over again. But nodes 3 and 4 can't run until there's 10 data samples that are ready. Once you have that FIFO queue that has been filled up, because node 2 in this case has run 10 times, at that point, then these 2 successor nodes can run. So that's the model. And now what we want to do is take this model and figure out how is it that we can apply those concepts and figure out what those GNU or the sketch deadline parameters should be. Now, in traditional real-time scheduling, that's like aimed at like the aviation or the automotive case. It's more thinking about control systems. And in control systems, oftentimes you have a frequency that's maybe 10 hertz, 30 hertz, 100 hertz, which is maybe fast for automotive application where you have more processing to do within each invocation. But that's a very slow rate in a signal processing application. And so there's a mismatch between some of the assumptions that exist in a control system and in signal processing. And so that's how we have to extend some of these models to be able to better reflect what's actually going on when you have data that's streaming in at such high frequencies. And so an important observation is that when you're doing this thread per block approach, every time you're switching from one block to another, there's overhead associated with doing that. You have to have a context switch, you have to flush out caches, all of this. And so there's a big cost to that, which if you're doing this at 10 hertz or 100 hertz, maybe isn't that significant. But if you're doing that in the gigahertz range, the megahertz range, then that overhead is really going to kill you. So you have to batch these samples and do multiple samples in one block, and this is done in GNU Radio. But what we want to do is figure out how is it that we can identify what those batch sizes should be to trade off latency and throughput, and then apply real-time scheduling to figure out what those latency and throughput guarantees can be. So with that, I'm going to let Simon talk about the experiments that he's run. Go ahead, Simon.
Yep. Hi, everybody. I'm going to take over from this point. So with all these ideas in our mind, we have done some experiments with the GNU Radio. The very first one we've done is execution time versus batch size experiment. It is we did a linear regression, and the y-axis is the clock cycles. The higher it is means the higher execution cost it is, and on the x-axis it's the numbers of samples consumed. From left to right means the increased number of samples consumed. As we can see that the result of the linear regression is pretty like linear, and we've done similar experiments for different blocks. We tried several different popular blocks from frequency shift, multiply const, add const, and decimator. We see like the similar trend holds like generally in the built-in blocks. What we can observe here is that we have an approximately linear relationship. Taking the frequency shift as an example, the cost to execute the first example is 8,800 clock cycles, while the cost to execute each sample after is only like adding 2 clock cycles each sample. So what it means is that the computational cost of initialization really dominates the whole cost. So what can we do with this finding? We constructed a marginal cost model. So we want to find the relationship between execution cost, initialization cost, and marginal cost. Since it's linear, we have like equation that E, execution cost, equals the initialization cost plus the sample size multiplied by the marginal cost delta. These results and this model reflects why GNU Radio batches samples per block invocation. With that finding, with that marginal cost, what can we do? Or what is the potential of this model? We came up with an idea of intra-block batching, which is like we are enabling more invocation of the same block to be executed at one time. The GNU Radio experiments showed that the initialization cost is way larger than the marginal cost by a factor of 100 to even 1,000 times, which means that maybe we can batch jobs to reduce the number of initialization costs needed to do the same amount of work. We also want to batch jobs predictably to apply real-time analysis and yield bounded latency, which is very important in real-time systems. A constant number of samples allows us to compute the execution cost using our marginal cost model we just created. And the GNU Radio, but the GNU Radio is non-deterministic in the number of samples processed. So this leads to a question. If constant, how many samples should we batch? So this is a figure to show what the execution time or execution cost will look like before we do a batch. We can see that 3 invocation of a task may cost like 3 initialization cost. However, if we can batch them, maybe we only have to pay 1 time for the initialization cost, which is a huge win in terms of execution. So let's dig a little bit deeper into this, the intuition for our marginal cost model's benefit. So for our intra-block batching, still the same example. On the left is the execution time before batching, and on the right is the execution time after batching. Taking conservative estimates, which means the ratio between the initialization cost and the marginal cost, let's suppose that the initialization cost is 200, and the marginal cost delta is 1, and the P is 400. Then the utilization, which is defined as the fraction of CPU time a task set demands, changes from left utilization before batching, which is the initialization cost plus delta divided by P, which is about 0.5. And after batching, the difference lies in both we are timing the marginal cost by 3, and also we're timing the P by 3, because we are now combining them together, and all our computing resource can be applied to this. So which makes the utilization to drop dramatically from 0.5 to 0.169. And we also came up with a different way to utilize this marginal cost model, which is called inter-block batching. So for intra-block batching, we are enabling multiple invocation of the same task, which is 1 block, but multiple times. However, for inter-block batching, we're trying to merge different blocks together to make them somehow like a super block. Let's say there are 2 different blocks, different jobs there. What if we can batch them like this? Can we also gain a win by saving the initialization cost? How would the marginal cost become? How would it change? Would it be just the arithmetic sum of those 2 marginal costs together? This is our intuition, and we will find out it later in our evaluation section. So we have all these ideas of batching jobs or batching tasks together. What are the techniques we want to use? So if we think about we just want to put more jobs together, as many as possible, the most naive or the easiest way is to do a uniform batching. We just multiply everybody by a same constant, and nothing changes. However, that can increase the latency, and sometimes it might not be the optimal way for us to batch. So we found a smarter way coming from the PGM graph. Looking at the graph and focusing on the 2 edges in a circle, in the 2 circles, the edge from node number 2 to node 3 and node 2 to node 4, on those two edges, the produce amount equals 1 and the consume amount equals 10, which indicates that node 2 needs 10 invocations before node 3 and node 4 can execute, because we need to fill up the FIFO queue before we can fire node 3 and node 4 to execute. Which means that rates of node 2 is 10 times higher than node 3 and 4. Which further means that huge initialization cost was paid by node 2. So what if we can batch node number 2 by a factor of 10? Then the PGM graph would look like that. The consume amount flowing into node number 2 turns from 1 to 10, and the produce amount on its two outgoing edges also changes from 1 to 10 because we multiplied them by a common factor of 10. What are the consequences by us doing such kind of batching? The rate of node number 2 decreases by a factor of 10 because now we need the consume amount is now 10, which means that 10 invocations of node number 1 now fires 1 invocation of node number 2. But the rates of node 2's successor nodes, which are 3 and 4, aren't affected. And we have reduced utilization without impacting the output rate, consequently. And we also increase the latency to buffer samples before node 2 can run, which is on the edge from 1 to 2. So this is for intra-block batching. What about inter-block batching? We want to do interblock batching because we want to further batch by merging multiple blocks into one super block. By doing this, we think that we can have fewer context switches, and we have better cache reuse, and we have reduced overhead with same marginal cost. This is the same example. We will show two different possible ways for interblock batching. The first one is batching the serially connected block together, like this. 2 and 5 now becomes a super block. And there can also be a different way of batching the two parallel blocks together. Now 3 and 4 becomes a super block. So this can only be manually done in GR4, but interblock batching can be more easily supported in GR4, which is great news for us. So now comes to the evaluation part. The GNU Radio support for early deadline first scheduler. Our batching techniques now allow calculation of deterministic execution cost. And the existing research from a different lab provides methods to derive appropriate deadlines. This enables us to assign deadline and execution cost to each flow graph task. The reason why we want that deadline and execution task is that we want to further apply them to the Linux level. So we can use the Linux level scheduler and turn our GNU Radio flow graph to a Linux scheduler acceptable type of task set. And these parameters will be passed before thread runs. So the Linux can then enforce real-time scheduling, giving GNU Radio task bounded latency and throughput guarantees using real-time analysis techniques. Once again, bounded and guaranteed are top 2 favorite words from our field. And we have some intra-block results. This is a graph with both utilization versus batch size and latency versus batch size. On the x-axis is from left to right is increasing the batch size, and on the y-axis from top to bottom is lowering the utilization, noting that lower utilization means better here. And on the y-axis, also, the lower the latency it is, the better performance we have. And from bottom to top, we are increasing the analytical latency bound. Note that this is the analytical, not the observed latency bound. Each point is an average over 1,000 we randomly generated PGM graphs using execution times from GNU Radio experiments. So what can we observe from our results here? The latency bounds grows linearly, diminishing returns in reducing utilization. And our rate exploiting batching further reduces utilization with relatively small impact on latency, which is great. So we can see there can be some sweet point that we want. For example, batching by a factor of 4 drops utilization from 6 to 2 with only 0.06 millisecond latency penalty. This result supports that system engineers can use a similar analysis to minimize utilization subject to a latency constraint. And we also have the results for interblock. Before we merge everything, and it's kind of like impossible for us to merge for every generally randomly created PGM graph. But we have done a similar linear regression results here. The two most basic built-in block we used is the AdConst and the frequency shift, which is the yellow line and the green line. And the purple line we have there is the arithmetic sum of those two blocks, like separate performance. And the only linear regression here is the performance of the merged block. On the x-axis from left to right is increasing the numbers of samples consumed, and the y-axis means the execution cost. Still, the higher clock cycle on y-axis means higher execution cost. And another thing to note that is higher intercept implies higher initialization cost, and a larger slope implies higher marginal cost. We can see we have a huge win in terms of the execution cost compared to naively adding them together. We've also done a case study to make it more practical. We still the narrowband FM receiver. We can see that on our graph, when we increase the batch size, we are decreasing the utilization, but we are also increasing the latency. But this is pretty representative and is similar to the trend we observe in our randomly generated results, which means that the latency and utilization trends still hold in a real GNU radio system. So in conclusion, we validated the marginal cost model for batch sample processing in GNU radio, and we presented two different batching techniques, one intra, one inter, and we evaluated randomly generated synthetic task systems to demonstrate a utilization latency trade-off. And we compared performance of GNU radio built-in blocks and their inter-block batching superblocks. Last but not least, we extended the GNU radio to support Linux sketch deadline and presented a case study applying the marginal cost model and batching a real signal processing application. Yeah, these are our contribution. Like we said, we are not a signal processing expert, but we are happy to contribute to this field. And in the future, we want to also contribute to the GR4, and we are also happy to try how our findings apply to the GPU or accelerators. We are happy that we can be part of this community. We're open to collaborations, and we believe that we have a shared goals to make the GNU radio better. Yeah, thanks everybody for listening.
All right, do we have any questions in the audience? Hold on.
So that the last graph on the lower right there, that's with your modified deadline scheduler, and and that's the x-axis is the batch size, but did you compare it to the unmodified scheduler?
Unmodified scheduler?
Just the standard scheduler that's in GNU Radio?
Oh, so we are not changing how the schedulers are implemented. We are somehow changing how we are changing the parameters of each task. So like the scheduler stay the same, but now we are, for example, still the same PGM graph, but the parameters of the PGM graph are different.
Okay, but did you, I see, so in the absence of your work, which point on that graph are we using?
The batch size equals 0.
Batch size equals 0. Oh, okay, so.
So the big difference is that these are analytical bounds on our utilization and latency. And so in GNU Radio, like stock, then you're not going to have any latency bound. And so we're not comparing because GNU Radio doesn't provide a latency bound that can be computed. So
These are bounds. This is not like an experimental measurement.
right, so these are analytical bounds rather than like observed latency.
I see,
utilization.
okay.
Yeah. But yeah,
Cool.
you're right. That would be an interesting thing to compare, and we should do that from an observed case. Yeah.
Yeah, this looks very promising.
Cool.
All right. Other questions? Hold on.
Hi. So you were talking about the PGM graph and how you can batch serial nodes together and parallel nodes together. Were you using the PGM graph to decide which batching operations you do?
Yeah.
Okay.
So for our rate exploiting batching, we are doing it like a reverse topological way from the from the sync node to the source node. And first, we want to apply. We can first apply the uniform batching, and then after applying like a shared factor, then we again apply the rate exploiting batching. So yeah, we are using the PGM graph to decide how we want to batch.
Thank you. Yeah, I'd like to learn more about that later.
All right. Other questions from the audience? All right. Let's give a round of applause. Thank you guys very much. So as I mentioned earlier, we are finishing up today. I was going to put some slides together, but and caught up closer than I thought. But a few things to stick around for. So the capture the flag is set to end in about half hour or so, and it's pretty close. So if you haven't had a chance or you're interested in how it's going, I highly recommend going to check out the Capture the Flag room. The other cool thing about Capture the Flag is that even though the official contest will end, the challenges will stay up. So even if you go over there and right now learn about some of the flags and those things, you can still play around with them. They'll also be tomorrow afternoon on our